Part 1. Sinosauropteryx. Stomach contents preserved within its ribcage show crushed remains of small lizards and early mammals, proving that Sinosauropteryx was an opportunistic hunter, not merely a scavenger. Its hunting strategy likely involved stealthy stalking followed by a rapid lunge, its long tail counterbalancing every movement, its keen eyes locked on a darting lizard. In this role, it mirrored the ecological niche of small mammalian predators today, controlling populations of insects and small vertebrates, supporting the balance of its ecosystem. The precision of its teeth, the flexibility of its neck, and the quick reflexes of its limbs combined to create a predator both efficient and graceful in miniature form. Reconstructing Sinosauropteryx's appearance depends on a fusion of fossil detail and modern imaging. High-resolution scans reveal attachment points for each filament, mapping the contours of its downy coat. Comparative anatomy with modern birds and crocodilians informs the orientation and density of these proto-feathers, allowing artists and scientists to collaborate on lifelike models. Such syntheses of evidence bring the creature into 3 dimensions, its bristly coat and slender limbs animated in digital realms. One can almost hear the soft rustle of filament against leaf, as the animal pauses beneath a canopy of damp ferns, breathing gently in a world lost to time, yet brought to vivid life through modern technology. Beyond its own lineage, the discovery of Sinosauropteryx unlocked a cascade of feathered revelations. Similar filaments emerged in dozens of other non-avian theropods, and even in some herbivores, tearing down the old concept that scales defined dinosaur skin. Feathers began as simple thermal and display structures, then evolved through myriad forms, culminating in the flight-enabling wings of birds. Each new fossil, Compsognathus, D. long Joravenita, adds nuance to this evolutionary tapestry, yet Sinosauropteryx remains the icon that first revealed the hidden plumage of dinosaurs. Its legacy echoes in every feather we see on a modern sparrow or eagle. The volcanic ash beds of the Ixian Formation represent a natural time capsule. Sudden eruptions buried entire ecosystems in moments, preserving animals in lifelike detail. These seasonal wetlands teemed with conifers, ginkgos, ferns, and early flowering plants, supporting a rich community of dinosaurs, mammals, amphibians, and insects. Sinosauropteryx was one delicate thread in this vibrant tapestry, its life woven among ancient trees and shallow lagoons. When you imagine these silent ash falls, consider how they immortalized the soft filaments of a tiny dinosaur, enfolding them forever in stone. Today, cutting-edge methods like synchrotron imaging and molecular archaeology tease out keratin signatures from minute fossil fragments, refining our understanding of how early feathers grew and functioned. These techniques hint at structural details, filament cross-sections, growth patterns, pigment distributions, offering clues to the behavior and ecology of long-vanished creatures. With each new insight, we draw closer to the living world of Sinosauropteryx, its downy form flickering to life in our scientific imagination, just as it once flickered in the dawn light of a lost world. As twilight fell over Cretaceous wetlands, Sinosauropteryx would slip beneath sheltering ferns, its proto-feathers ruffling softly in the evening breeze. In that hush before night fully descended, this emblem of ancient innovation stood as a serene herald of feathered beginnings. Its simple, elegant filaments, once warm and vital, remain forever immortalized in stone, guiding us gently toward a restful, dream-filled slumber. In the early Cretaceous, about 12 million years ago, the tiny theropod Sinosauropteryx prima stalked the lake margins and fern-lined wetlands of what is now Liaoning province in northeastern China. Its lightly built skeleton and filamentous dino fur were exquisitely preserved in catastrophic ash falls, granting a rare glimpse at skin impressions alongside bones. At just over a meter long and under a kilogram in weight, Sinosauropteryx ranked among the smallest known non-avian theropods, yet it carried the world's first clear proof that simple feather-like structures were not exclusive to birds. These unbranched, hair-like proto-feathers carpeted its neck, back and tail, hinting at an insulating coat far more complex than mere scales. When first described, this discovery revolutionized paleontology, collapsing the old divide between scaly dinosaurs and feathered birds, and revealing that feathers had deep dinosaurian roots long before they ever lifted a creature into the sky. Its body plan combined sprint-capable limbs with a tail nearly as long as its torso, creating an agile frame built for short bursts of speed and quick turns through dense undergrowth. Sinosauropteryx possessed short, grasping forelimbs, perhaps used to handle small prey, and powerful hind limbs that propelled it with surprising swiftness. Tiny, recurved teeth lined its narrow jaws, perfectly suited for capturing insects, small lizards, and early mammals that scurried beneath the foliage. Perhaps most striking was its banded tail, fringed with alternating dark and light filaments that would have broken up its outline in the dappled light of shoreside reeds, rendering it all but invisible to both predator and prey. Imagine the sunlit reeds shimmering in a breeze as this miniature hunter slipped silently among them, proto-feathers rippling like a living brushstroke across an ancient canvas. The proto-feathers themselves were simple, unbranched filaments, stage 1 structures in the story of feather evolution. Originating likely for thermal regulation, these filaments trapped a layer of warm air close to the skin, vital for a small, warm-blooded creature in temperate climates. Over time, these same filaments would evolve branching patterns, eventually giving rise to the complex flight feathers of birds. Chemical studies of melanosome-like structures preserved in Sinosauropteryx fossils even reveal subtle color patterns, rusty orange bands alternating with pale stripes that brought this little dinosaur to vibrant life. Such reconstructive work transforms our view. Rather than a dull gray reptile, we see a vividly colored animal, its proto-feathers shimmering in morning light, like a tiny prehistoric tapestry. Part 2. Anchiornis. In the shadowy forests of what is now northeastern China, during the late Jurassic period over 160 million years ago, a small feathered creature darted through the underbrush and leapt from branch to branch. This was Anchiornis, a dinosaur no bigger than a pigeon, yet full of significance in the story of flight. Its name means near bird, and it lived up to that title in more ways than one. This tiny dinosaur was covered in complex feathers and bore an anatomy that was strikingly transitional, a beautiful bridge between ancient theropods and the birds we see today. Though Anchiornis lacked the strong chest muscles needed for powered flight, its long feathers on both its arms and legs hinted at a very different kind of movement, perhaps gliding, parachuting, or something in between. It wasn't just another small theropod. Anchiornis was a symbol of evolutionary experimentation, a creature evolving new ways to interact with the world above the ground. What sets Anchiornis apart isn't just its size or even its feathers. It's the exquisite preservation of its fossils, which have allowed paleontologists to reconstruct its plumage in extraordinary detail. The fossil beds of Liaoning Province, where Anchiornis was discovered, are famous for yielding astonishingly complete and delicate specimens, sometimes including traces of soft tissue. In the case of Anchiornis, scientists were even able to determine the color patterns of its feathers by analyzing microscopic structures called melanosomes. These pigment-bearing organelles gave away an ancient color palette: black and white wings, a gray body, and a reddish-brown crest on its head. It's mind-boggling to consider that we can glimpse, with relative confidence, the actual color patterns of a creature that lived so long ago, an animal that wore a sharp tuxedo-like coat of feathers while leaping among trees, long before birds ever flapped their wings. Anchiornis also had a uniquely feathered anatomy that sets it apart from other early feathered dinosaurs. It had large veined feathers not only on its arms, but also on its hind legs and tail, creating a kind of four-winged structure. These weren't just fluff for insulation, they had aerodynamic properties. Some scientists believe that Anchiornis could have used its limbs to control its glide, or help it balance during leaping descents. Its legs were long and slender, ideal for climbing and hopping, while its arms were proportionally longer than in most non-avian dinosaurs of similar size. Unlike modern birds, it still had clawed fingers and a long bony tail, showing that it hadn't yet completed the journey toward full avian form. But with each generation, natural selection may have honed features that offered survival advantages in the canopy-rich world it inhabited. This dinosaur's lifestyle remains a fascinating mystery. Living in densely vegetated forests, Anchiornis likely preyed on insects, small vertebrates, and perhaps even soft fruits or plants. Its agile build and likely excellent balance would have made it a skilled climber and jumper, and its gliding or parachuting ability might have allowed it to move between tree trunks with little need to descend to the forest floor, where predators might lurk. Imagine a world of towering conifers and primitive ferns, where this creature hopped from shadowed branch to sun-dappled vine. Anchiornis didn't just live. It navigated a complex vertical world. It had to remain alert to larger carnivorous dinosaurs stalking through the forest floor, and it had to find clever ways to move quickly, efficiently, and quietly through the dense canopy above. Anchiornis is also central to our understanding of how feathers first evolved. Long before they were used for flight, feathers likely developed for other purposes: insulation, display, camouflage, or even sensory feedback. Anchiornis shows us an intermediate stage, feathers that were already complex in form and color, but not yet used for sustained flight. This challenges the traditional view of feathers as being an invention solely for flying. It reminds us that evolution doesn't always have a clear-cut direction. It tinkers, repurposes, and reshapes over time. In Anchiornis we see that feathers may have first been tools for temperature control or visual communication, long before becoming the sophisticated airfoils that would carry birds across the skies. One of the most enchanting aspects of Anchiornis is how much of its appearance we know with confidence. In the past, dinosaur reconstructions often required heavy guesswork, and color was almost entirely speculative. Anchiornis changed that. It was one of the first dinosaurs whose color patterns could be accurately reconstructed, giving researchers and artists alike a rare glimpse into prehistoric aesthetics. That reddish crest may have been used in courtship or for identifying individuals within a group. Its bold wing stripes and monochrome palette could have helped it blend into dappled forest light or startle predators. This was a creature of contrasts, both in coloration and in what it represents, the delicate balance between ancient and modern, earthbound and airborne. While Anchiornis wasn't a bird, it lived just before the appearance of Archaeopteryx, often dubbed the first bird. Both creatures shared many similarities, but Anchiornis came slightly earlier and helps to fill in the evolutionary story leading to modern birds. It existed during a time when flight was still experimental in nature, Different species tried different methods of moving through the air. Anchiornis's gliding adaptations represent one of those paths, a possible evolutionary dead end, or a stepping stone toward greater aerial capability. Either way, it plays a vital role in helping us understand how natural selection operated on small, feathered dinosaurs exploring the world above the ground. Night in the Jurassic forest must have been quiet, punctuated by the occasional rustle of leaves or distant call of another creature. Anchiornis, with its agile limbs and light body, likely took shelter among the higher branches, feathers puffed to trap warmth against the cool air. These nocturnal habits may have helped it avoid larger predators, and its muted colors would have helped it blend into moon-dappled foliage. It's peaceful to imagine a tiny creature curling into a feathered ball beneath a leafy canopy, dreaming under a blanket of stars that shone over a world long vanished. Anchiornis reminds us not only of how flight came to be, but how life adapted in delicate and intricate ways to survive. Today, when birds flit past our windows or sing from rooftops, their ancient roots go deeper than we might expect. The humble sparrow or jay carries echoes of Anchiornis, a tiny dinosaur that paved the way for an entire branch of life that would someday fill the skies. Each feathered wing beat is part of a story that began in a time before time, in forests of shadow and light, where creatures like Anchiornis tested the very boundaries of what it meant to live not just on the ground, but above it. Part 3: Microraptor. In the mist-shrouded treetops of northeastern China, around 120 million years ago, a glimmer of midnight black flickered among the branches. This was Microraptor gui, a raven-sized dromaeosaur whose 4 wings, a pair on its arms and a surprising pair on its legs, allowed it to slip silently between the ancient conifers. Far more than a feathered curiosity, Microraptor represents one of the earliest experiments in dinosaurian flight. With delicate, iridescent plumage and an anatomy perfectly balanced for aerial agility, it redefined the boundary between ground-bound hunter and airborne navigator. Its discovery in the early 2000s electrified paleontology, revealing that feathers were not just decorative or insulating, but functional structures evolving long before the first birds took to the skies. Measuring roughly 60 centimeters from snout to tail tip and weighing little more than a modern crow, Microraptor combined a lightweight frame with bone, crushing strength in its jaws. Its body was covered in a mosaic of feathers, from fuzzy down near the torso to long, aerodynamic remiges on its forelimbs and hindlimbs. Unique among known dinosaurs, its hindlimb feathers formed an additional wing surface, creating a 4-winged configuration that baffled early researchers. The legs themselves were held in a sprawled posture during gliding, with long feathers projecting laterally, an arrangement that suggests Microraptor may have leapt from heights and controlled its descent in a graceful wing-assisted glide rather than powered flight. Fossil evidence from the Liaoning deposits preserves these feathers in astonishing detail, revealing the overlap, curvature, and asymmetry of flight feathers. The primary feathers on both arms and legs exhibit the aerodynamic contours necessary for lift generation, while the tail feathers formed a stabilizing rudder. Wind tunnel models and computer simulations have tested Microraptor's flight capabilities, suggesting it achieved impressive glide ratios, able to cover distances of tens of meters with minimal height loss. These studies underscore how Microraptor exploited a rich, 3-dimensional habitat, an ecological niche, where gliding between trees provided both efficient locomotion and a stealthy hunting platform. Color reconstruction has added another layer of wonder. Microscopic examination of melanosomes, pigment, containing organelles preserved within the feather impressions, revealed a predominantly glossy black plumage with possible subtle iridescence. This sheen would have served multiple functions: camouflage within the dimly lit forest undergrowth, signaling to mates or rivals, and perhaps even thermoregulation by absorbing solar warmth. Such vivid coloration underscores the complexity of dinosaur integument and hints at sophisticated visual communication among feathered species long before true birds emerged. The mechanics of Microraptor's takeoff and landing remain subjects of lively debate. Some researchers argue that it launched from the ground with explosive jumps, flapping its forewings to gain altitude before transitioning to an extended glide. Others propose a pure tree launch model, where it leapt from heights and then used its forewings to maneuver in the air with fine control. Either scenario speaks to evolutionary ingenuity. Microraptor illustrates a transitional step in wing use, a backup plan for survival in a world still dominated by terrestrial predators and populated by arboreal prey. Dietary evidence complements this aerial prowess. Stomach content fossils reveal fish scales and the remains of small birds, lizards, and mammals, indicating that Microraptor was an opportunistic feeder. Its curved, serrated teeth and strong foreclaws enabled it to snatch slippery fish from shallow streams or ambush small creatures on tree branches. This versatility suggests that Microraptor exploited both aquatic and arboreal resources, a flexible foraging strategy that would have been essential in the dynamic ecosystems of the early Cretaceous. Though direct evidence of social behavior is lacking, anatomical comparisons with other dromaeosaurs hint at possible flocking or communal roosting. Group living could have enhanced hunting success, increased protection for juveniles, or facilitated complex mating displays. High-density fossil sites and trackways in similar formations occasionally preserve multiple individuals together, raising the tantalizing possibility that Microraptor sometimes moved in loose aggregations, its four-winged forms casting fleeting shadows under the prehistoric canopy. Microraptor's world was a landscape of volcanic lakes, braided rivers, and dense conifer forests, punctuated by sudden ashfalls that entombed creatures in moments. These extraordinary Lagerstätten preserve not just bones but soft tissues, feathers, and even stomach contents, offering a detailed portrait of life in deep time. Envision a forest alive with the calls of early birds, the rustle of fern fronds, and the silent glides of feathered dinosaurs weaving through shafts of sunlight. In this realm, Microraptor perfected the art of controlled descent, a pioneer of the skies before the age of birds truly dawned. In reflecting on Microraptor, the mind drifts beyond mere anatomy to the elegance of evolutionary experimentation. Here was a creature that blurred the lines between reptile and bird, ground and air, function and form. Its legacy whispers through every downy feather and every gliding silhouette, reminding us that the story of flight is one of countless small innovations, momentary trial and error, and the unceasing drive of life to explore new frontiers. As the ancient sun set on those Jurassic forests, Microraptor soared on invisible currents, guiding the world toward a future where the skies would belong to birds. Part 4. Archaeopteryx. In the early Cretaceous forests of northeastern China, about 125 million years ago, a small theropod named Archaeopteryx roamed the damp undergrowth. Its name, meaning tail feather, hints at its most striking feature, a fan of symmetrical feathers fanning from the end of its stubby tail. Measuring barely a meter from head to tail, Archaeopteryx combined a dinosaur's toothless beak and powerful hind limbs with an unexpected coat of feathers on its arms, tail, and body. This creature laid bare the fact that feathers existed long before flight, serving roles beyond mere aerodynamics. Its discovery in the fossil-rich Yixian Formation revealed detailed impressions of downy body feathers and mature tail and arm plumes, a combination of insulation, display, and evolutionary experimentation. The moment those fossils were unearthed, the world's vision of dinosaurs changed. No longer scaly monsters, they had donned intricate plumage in deep time. Archaeopteryx's anatomy strikes a balance between primitive theropod and nascent bird. Its skull was short and wide, ending in a keratinous beak lacking teeth, while its neck was long enough to forage ground, level plants or sift through leaf litter. Underneath, a relatively large belly, sometimes containing gastroliths, speaks of a digestive system adapted for grinding tough vegetation and small prey. Powerful hind limbs, built for running, contrasted with its small forelimbs, which bore long, stiff feathers but lacked the wrist flexibility for flapping flight. The hips and pelvis reveal a posture that was neither fully erect nor sprawling, suggesting a graceful, ground-dwelling gait. In life, Archaeopteryx moved with the confident rhythm of an animal, perfectly adapted to forest floors, ever alert for insects, seeds, and the occasional lizard hiding beneath ferns. The feathers of Archaeopteryx were a study in early plumage diversity. Body feathers were simple, filamentous down, soft and insulating, while wing feathers were symmetrical and blade-like, forming a stiff fan incapable of powered flight, but ideal for display or terrestrial balance. On its tail, a remarkable array of 10 long plumes spread outward, creating a near-circular fan that lightly caught evening light in dazzling patterns. The combination of down and pennaceous feathers implies multiple roles, keeping the dinosaur warm on cool nights, signaling health or maturity to potential mates, and perhaps even allowing Archaeopteryx to steer itself during rapid turns or hops across the forest floor. These feathers represent an important stage on the path from simple integument to the complex flight feathers of later birds. Beyond display and insulation, these feathers may have played a sensory role. In modern birds, specialized feathers on the legs and tail help detect air currents and subtle vibrations. Archaeopteryx's plumes could have similarly provided feedback while navigating through dense vegetation or avoiding predators. The arrangement and density of feathers suggest a fine-tuned system for perceiving the environment, each plume a tiny antenna, picking up the rustle of leaves, the approach of a stealthy predator, or the movement of a fleeing insect. This sensory hypothesis reveals feathers as multifunctional structures long before they took on aerodynamic refinement, a testament to nature's ability to repurpose existing tools for ever-widening tasks. The toothless beak of Archaeopteryx points to an omnivorous diet. Microscopic wear patterns on its jaw indicate it chewed both plant material and small animals, using the beak to nip buds, fruits, and tender shoots, while also cracking the exoskeletons of beetles or seizing small vertebrates. Within its thoracic cavity, polished gastroliths, stomach stones, have been found in some specimens, confirming that it swallowed grit to help grind fibrous food in a muscular gizzard. This fascinating combination of features, a bird-like beak, stomach stones, and a digestive system capable of processing both vegetation and protein, underscores how Archaeopteryx occupied a flexible ecological niche, thriving on the abundant resources of its floodplain home. The environment it inhabited was a mosaic of wetlands, volcanic ash beds, and coniferous forests, where cycads and horsetails grew thick along riverbanks. Occasional ash falls buried entire communities in moments, preserving not only bones but delicate feathers and even footprints. In this dynamic habitat, Archaeopteryx faced both opportunity and danger, predators like Sinornithosaurus and aquatic threats from large fish lurked nearby, while seasonal floods and volcanic events reshaped the landscape. Its combination of agility, sensory-rich plumage, and dietary adaptability allowed it to flourish, illustrating the remarkable resilience of small dinosaurs in the ever-changing tapestry of Cretaceous ecosystems. Social behavior in Archaeopteryx remains speculative, but nesting sites and group fossil occurrences hint at communal living. Some bone beds contain multiple individuals of varying ages, suggesting that these dinosaurs may have nested or foraged in loose aggregations. Group living would have provided added protection to juveniles, whose down-like feathers offered imperfect insulation and minimal defense. Adults with fully developed tail and arm fans might have engaged in elaborate courtship displays, fanning their plumes, bobbing their heads, and creating a flickering spectacle of feathers in golden light as a prelude to spring mating rituals. In the grand sweep of evolution, Archaeopteryx stands as a vital waypoint on the road to modern birds. It belongs to the oviraptorosaurs, a lineage that blurs the traditional boundaries between reptiles and birds. Its mix of beak, feathers, and gait reveals a complex story of divergent paths and convergent solutions. While it never mastered flight, its feathers laid the groundwork for the aerodynamic leaps of later paravians. In the fine details of its plumage and the shape of its pelvic girdle, the blueprints of avian success can be traced, showing that every clade contributes threads to the vibrant tapestry of life. As dusk settled over the ancient floodplains, Archaeopteryx would tuck its fans into a snug display, feathers glinting with latent color as twilight deepened. Cradled in the hush of prehistoric night, this feathered pioneer embodied the patient artistry of evolution, each filament a brushstroke in a masterpiece spanning millions of years. Its story, etched in stone and preserved in the ash, whispers of a world where feathers first unfurled, not in pursuit of the skies, but as instruments of warmth, sensation, and beauty, a quiet herald of the dawn of birds, guiding minds toward restful dreams. Part 5. Yutyrannus. In the early Cretaceous forests of Liaoning Province, China, around 125 million years ago, stalked a predator unlike any other, Yutyrannus huali, the beautiful feathered tyrant. This colossal theropod stretched nearly 9 meters from snout to tail and tipped the scales at over a ton, yet its bones were sheathed in a coat of downy filaments. 3 nearly complete specimens, preserved in volcanic ash beds, reveal that even gigantic predators relied on feathers for warmth and display. Picture a massive skull, bristling with serrated teeth, framed by a shaggy mane of pale feathers, an image that forever altered the perception of dinosaur integument by showing that plumage extended far beyond the realm of small flight-related species. The feather types on Yutyrannus varied dramatically across its body. Simple, hair-like filaments covered its flanks and belly, providing insulation against seasonal chills. Along its spine and hips, thicker tufts formed a low crest that rippled when the animal moved. Longer, more quill-like feathers sprouted from its forearms and the base of its tail, hinting at roles in social signaling. Envision a group of these titanic theropods gathering at dawn, beneath towering conifers, crest feathers raised in silent display, lit by shafts of red morning light. Their plumage would have conveyed health, status, and identity to rivals and potential mates alike. A living tapestry of color and form. Anatomically, Yutyrannus retained the signature traits of its tyrannosauroid lineage: a massive bone-crushing skull, powerful hind limbs built for weight bearing, and 3-fingered forelimbs that, though small in comparison, may have been used in courtship or combat. Pneumatic openings in its vertebrae hint at an advanced air sac system, enhancing respiratory efficiency, traits reminiscent of modern birds of prey. Its tail, stiffened by elongated vertebral spines, provided balance and stability, while its robust pelvis supported a heavy torso. Each element of its skeleton speaks of both raw power and surprising lightness, a duality mirrored in its feathery coat. The Yixian ecosystem that Yutyrannus dominated was a world of wetland forests, seasonal rivers, and periodic volcanic ash falls. Conifers and ginkgos towered overhead, while ferns and horsetails carpeted the fertile floodplains. Herbivores like Psittacosaurus and Caudipteryx browsed with abandon, unaware of the down-coated giant moving silently through the shadows. Occasional ash eruptions blanketed entire valleys, entombing creatures in moments and preserving them in astonishing detail. In such a dynamic habitat, Yutyrannus stood as apex predator, its keen senses, stereo vision, acute smell, and sensitive integument, allowing it to track prey across varied terrain. Evidence of its diet is inferred from jaw structure and tooth wear rather than direct gut contents, but its massive serrated teeth and powerful bite suggest a preference for mid-sized dinosaurs and mammalian prey. Bone-crushing capability would have allowed it to access marrow and mineral-rich tissues, maximizing nutrition from each kill. Whether scavenger or active hunter, Yutyrannus combined stealth, strength, and environmental mastery to maintain its status at the top of the food chain. Its feathers, unlikely to aid in speed, may nonetheless have reduced noise as it advanced through vegetation, muffling its approach. Social interactions among Yutyrannus remain speculative, but the discovery of multiple individuals together hints at least occasional groupings. Juvenile and subadult remains alongside adult skeletons suggest that family groups or communal nesting sites may have existed. Feathered adults could have shielded hatchlings in nests lined with soft down, using their plumage as protective insulation. These parental behaviors, echoing those of modern birds, speak to an evolutionary continuity of brooding and care that predates true avian lineages. From an evolutionary standpoint, Yutyrannus occupies a pivotal position between earlier small, feathered tyrannosauroids and later giant tyrannosauroids. Its combination of primitive traits, such as long arms and a three-fingered hand, and derived features, like an enlarged skull and pneumatic bones, illuminates the pathway that led to apex predators such as Tyrannosaurus rex. The presence of feathers in this lineage suggests that even large-bodied tyrannosaurs may have retained plumage at certain life stages or in cooler environments, challenging the assumption that scaly hides were universal among giant dinosaurs. As twilight fell over those ancient woodlands, Yutyrannus would retreat to sheltered groves, its feathery coat trapping the fading heat of day. The hush of evening would be broken only by the distant calls of early birds and the rustle of conifer needles. In that quiet moment, the beautiful feathered tyrant stood as a living testament to evolutionary ingenuity, a creature that blended brute force with delicate plumage, forging new ways to thrive in a world perpetually on the brink of change. Part 6. Tianulongs. In the twilight of the Jurassic, around 160 million years ago, a small, enigmatic dinosaur darted among the undergrowth of what is now northeastern China's Tiaojishan Formation. Named Tianulong Confucius, heavenly dragon of Confucius, this roughly 1 meter long ornithischian combined a slender bipedal frame with an unexpected covering of filamentous integument. Its discovery in 2009 shocked paleontologists by revealing that primitive hair-like structures adorned not only theropods, but also the herbivorous side of the dinosaur family tree. Encased in fine volcanic ash, the holotype skeleton preserves rows of long, unbranched filaments along the neck, back and tail, suggesting that filamentous proto-feathers may have been an inherited trait of early dinosaurs rather than a unique innovation of bird ancestors alone. The anatomy of Tianyulong was as surprising as its plumage. Its skull bore a small, upturned beak, ideal for cropping vegetation, yet the jaws housed three distinct types of teeth: incisiform front teeth for snipping plants, conical caniniform teeth, perhaps for nipping harder material or defense, and cheek teeth adapted for grinding. This heterodont dentition, rare among ornithischians, indicates a versatile diet capable of processing a variety of foods, soft ferns, seeds, and possibly small invertebrates. The forelimbs were relatively short but strong, ending in 5-fingered hands, whereas the long, powerful hind limbs supported a swift, agile gait. A stiffened tail, counterbalancing the torso, enabled nimble turns among low-lying vegetation. The most striking feature of Tianyulong was its filamentous coat. Along the neck and down the dorsal column, simple, hair-like filaments reached up to 10 centimeters in length, forming a shaggy crest. Similar plumes extended along the tail, with the longest filaments brushing against the ground like a living banner. These monofilaments lacked the branching complexity of later bird feathers, yet their uniform arrangement and density hint at a functional pattern, not a random tuft. Darker tips on some filaments suggest subtle color variation, perhaps a pale brown base with darker shafting, a camouflage scheme that blurred the dinosaur's outline amid dappled sunlight and shadow. Such filamentous coverings likely served multiple purposes. In a habitat marked by seasonal fluctuations, cool, misty mornings and warm afternoons, these proto-feathers would have provided insulation, trapping a layer of warm air close to the skin. In social contexts, long neck and tail filaments could have been erected in displays of dominance or courtship, forming shimmering plumes that caught the light and signaled fitness to mates or rivals. The sensory hypothesis posits that these filaments aided in detecting subtle air currents or ground vibrations, enhancing Tianyulong's awareness of approaching predators or the rustle of potential food. Together, these functions underscore how early feathers were versatile tools long before true flight evolved. Phylogenetically, Tianyulong sits as a basal heterodontosaurid, a small ornithischian lineage once thought confined to southern continents. Its presence in Asia extends the group's known range and highlights a more complex biogeographic history. Most importantly, the presence of filaments in Tianyulong, a distant cousin of armored and horned dinosaurs, suggests that the common ancestor of all dinosaurs might have been feathered. This challenges earlier models that restricted primitive feathers to theropods, indicating instead that scales and feathers coexisted across multiple lineages, with integument evolving in myriad directions to suit different lifestyles and climates. The paleo-environment of the Tianyugeshan Formation was dynamic volcanic ash beds, interleaved with lake sediments, paint a picture of long-dead forests, punctuated by sudden ash falls. Coniferous trees, ginkgos, cycads and ferns flourished in this temperate floodplain, providing abundant forage for herbivores like Tianyulong and its contemporaries, including the small therizinosaurs, Bipiosaurus, and carnivorous dromaeosaurs, such as Sinornithosaurus. Seasonal storms and volcanic activity shaped the landscape, creating both lush feeding grounds and lethal hazards, where a single eruption could blanket the forest floor, preserving entire ecosystems in fossil-perfect detail. Dietary habits in Tianyulong were likely as varied as its tooth types imply. Microscopic wear patterns on fossil teeth show scraping and grinding consistent with fibrous plant material, while occasional scratches hint at abrasive grit from soil and grit swallowed with low vegetation. Seed eating may have been a specialty, with the conical teeth cracking tough husks before grinding cheek teeth processed the meal. Opportunistic ingestion of insects or small vertebrates cannot be ruled out, given the probable omnivorous ancestry of heterodontosaurids. This dietary adaptability would have been crucial in a fluctuating environment, allowing Tianyulong to exploit multiple food sources when primary forage became scarce. Locomotion and behavior paint Tianyulong as a swift, alert runner, capable of short bursts of speed to evade predators. Its long hind limbs and lightweight body suggest a runner rather than a bulky grazer, while sternum and hip structure imply powerful leg muscles. Social dynamics remain speculative, but bone beds containing multiple individuals hint at group living, perhaps loose herds that foraged and nested communally. Family groups may have offered protection to vulnerable juveniles, their filaments fluffed in unison to deter smaller predators. These behaviors, while unconfirmed, evoke images of feathered clusters weaving through fern-filled clearings, an ancient ballet of survival and cooperation. In the cool dusk of a Jurassic evening, Tianyulong would huddle beneath conifer boughs, its filamentous coat trapping warmth as it settled into a low crouch. The forest would hum with insect chatter and distant calls of early mammals and pterosaurs settling for the night. In that quiet moment, feathers rustling softly and cooling air, the heavenly dragon embodied the ingenuity of evolution, a warm-blooded pioneer wearing a coat of prehistoric fluff. Though millions of years have passed, its legacy endures in every downy feather that ruffles in a modern bird's flank, a reminder that the boundary between reptile and bird was never as sharp as once imagined. Part 7. Archaeopteryx. Nestled within the fine ash beds of the Daehugu Formation in Inner Mongolia, a diminutive marvel of prehistoric life once thrived nearly 165 million years ago. Archaeopteryx measured scarcely 25 centimeters from snout to tail base, its fragile bones encased alongside impressions of extraordinary integument. This tiny theropod, whose name means display feather, carried 4 elongated ribbon-like tail plumes, feathers unlike any seen before in dinosaurs. Each plume, smooth and unbranched, extended far beyond the vertebral tips, creating a startling visual display that would have fluttered behind the animal as it moved. In a landscape punctuated by volcanic ash falls and conifer groves, these plumes likely caught shafts of light, forming living banners that flared in the forest gloom, signaling fitness and identity within dense undergrowth. Beneath these spectacular tail feathers lay a coat of simpler body filaments, hollow hair-like structures that provided insulation and a sensory interface with the environment. Their uniform distribution across the torso, neck and base of the tail suggests a mapped pattern rather than random tufts, hinting at an early stage in feather evolution where insulation and display coexisted. Fossil evidence indicates these filaments were anchored in tiny knobs along the skin, providing an anchor point that allowed each plume and filament to pivot with the slightest breeze. In cool, mist-laden mornings, this feathery covering would have trapped vital warmth, while in social encounters, the long tail ribbons could have been unfurled into an impressive fan to dazzle rivals or attract mates. The skull of Archaeopteryx was a delicate bird-like structure with large eye sockets implying keen vision suited for low-light conditions under the forest canopy. Its beak was slender and toothless at the front, sharpened for cropping vegetation, yet farther back, 6 pairs of small pointed teeth lined the upper and lower jaws. This heterodont dentition hints at omnivorous habits, snipping soft shoots, nipping at seeds and snapping up small insects. The juxtaposition of a beak with true teeth underscores an experimental toolkit of feeding strategies rarely seen outside specialized mammalian lineages, revealing evolutionary ingenuity in exploiting varied food sources without sacrificing cranial lightness. Adaptations for movement in Epidicipteryx bridged terrestrial agility with possible arboreal acrobatics. Its forelimbs were elongated relative to its body, each ending in 3 slender fingers tipped with recurved claws, tools for grasping branches or snaring insects. The hind limbs were robust yet agile, the ankle and hip joints optimized for rapid terrestrial locomotion or bounding among low foliage. A stiff tail, reinforced by elongated spinal processes, served as a dynamic counterbalance, allowing quick turns and precise footfalls. Though no true wing feathers have been preserved, the combination of long forelimbs, filamentous covering, and flexible joints suggests that Epidicipteryx may have performed controlled jumps or flutters, steering itself through a 3-dimensional world of tree trunks and fallen logs. Ecologically, Epidicipteryx inhabited a temperate monsoonal climate, where seasonal rains nourished a mosaic of lakes, wetlands, and mixed forests. Frequent ash eruptions entombed flora and fauna with stunning fidelity, preserving not only skeletons but soft tissues and feathers. Ginkgos and horsetails flourished alongside conifers, while volcanic activity periodically reshaped the landscape. Within this vibrant biome, small vertebrates from salamanders to basal mammals teemed among ferns, offering Epidicipteryx a smorgasbord of prey. Its dental versatility and nimble frame enabled it to exploit both plant and animal resources, shifting diet with seasonal availability, a survival strategy emblematic of small predators in a world dominated by ever-changing landscapes. Social behavior remains largely speculative but tantalizing. The striking tail plumes carried by Epidicipteryx suggest visual communication was paramount, perhaps during courtship displays beneath the fern-fringed twilight of Jurassic dusk. Bone beds occasionally preserve multiple individuals close together, hinting at least temporary aggregations. Brooding behavior may have been employed to protect vulnerable hatchlings, with adults shading nests beneath their filamentous coats. In the hush of prehistoric evenings, clusters of these tiny dinosaurs might have rustled softly among leaf litter, illuminated by shafts of volcanic light, a congregation united by instinctual choreography of movement and display. On a deeper evolutionary scale, Epidicipteryx occupies a pivotal branch near the roots of the Paravian lineage, illuminating pathways that led to both powered flight and elaborate display feathers in later avialans. Its mixture of primitive traits, such as clawed hands and a long bony tail, and derived plumage underscores mosaic evolution, where features evolved in modules repurposed over time for diverse functions. By examining Epidicipteryx, scientists glean insights into how feathers first arose not merely for insulation, but as signals honed by sexual selection, only later copied for aerodynamic prowess in the ancestors of birds. As dusk deepened and the forest floor cooled, Epidicipteryx would settle into sheltered hollows or low vegetation, tucking its delicate feathers close to conserve warmth. The gentle hum of night insects and the call of early mammals echoed through the trees, a soundtrack to a world only faintly familiar. In those moments, a small dinosaur with spectacular plumes stood at the intersection of reptilian might and avian grace, a living emblem of evolutionary possibility. Its ribbon-like tail feathers, once fanned in mesmerizing display, now lie silent in stone, yet their legacy endures in every fluttering plume that graces a modern bird. Generations of paleontologists have studied this tiny display specialist, yet Archaeopteryx still holds mysteries, none more intriguing than the exact biomechanics of its ribbon feathers. Recent biomechanical simulations suggest these elongated plumes could have been flicked or vibrated, much like modern birds use crests or wattles, creating subtle but distinct visual signals across the dim forest understory. Such nuanced communication, invisible to most predators but crystal clear to conspecifics, might have played a critical role in mate selection or social cohesion. In exploring Archaeopteryx, the boundaries between behavior, anatomy, and ecology converge, revealing a creature both delicate and complex, dancing on the razor's edge of evolutionary transformation. Part 8. Orornis. In the mist-shrouded forests of northern China, some 160 million years ago, a diminutive creature poised on the edge of avian evolution. Orornis sui, the dawn bird, was unearthed in the Qiaojishan Formation in 2013, challenging notions of which species truly took wing first. Measuring just over half a meter from snout to tail tip and weighing less than a kilogram, it combined slender limbs, a long bony tail, and a full coat of downy and pennaceous feathers. Its very name evokes the interplay of night and day, aurora, the first light, apt for a dinosaur that stands at the threshold between terrestrial theropods and the first flickers of flight. In fossil slabs where fine volcanic ash preserved every filament, Orornis emerges as a testament to an era when evolution's experiments in feathers and flight were just beginning to take shape. The skeletal anatomy of Orornis reveals a delicate balance of primitive and derived traits. Its skull was compact with lightly built jaws bearing small recurved teeth, ideal for a varied diet of insects and small vertebrates. The forelimbs were proportionally long, boasting an elongated humerus and ulna that suggest strong muscle attachments for feathered wings. Unlike later birds, its wrists lacked a fully fused semilunate carpal, indicating limited flapping capability, yet the robust coracoid and sternum hint at some degree of flapping strength. Its pelvic bones retained an ancestral configuration, while the hind limbs were adapted for swift terrestrial movement. Each limb and joint tells of a creature still grounded yet experimenting with liftoff, a living bridge between earthbound carnivores and the first true flyers. Feathers enveloped Orornis in a tapestry of function and form. Down-like filaments covered the body, providing essential insulation in a temperate climate marked by seasonal coolness and smoky volcanic air. Along the arms and the elongated tail, pennaceous feathers formed asymmetric veins capable of generating lift during glides or aiding in balance during rapid turns. Though far too weak for sustained powered flight, these feathers likely allowed Orornis to parachute from low branches, control its descent, and maneuver through dense foliage. The plumage's arrangement, thicker along the back ridge, tapering toward the sides, mirrors patterns seen in later avialens, suggesting that feather distribution was fine, tuned early on to support both thermoregulation and basic aerial control. Positioned phylogenetically at the base of Avialae, Orornis predated Archaeopteryx by a few million years, forcing scientists to reconsider the narrative of bird origins. Its discovery highlighted that features once thought unique to earliest birds, such as pennaceous feathers and semi-rigid tails, were in fact more widespread among small theropods. This redefined the Avialae clade, expanding its membership and pushing back the date of feathered flight precursors deep into the Jurassic. The evolutionary tapestry of dinosaurs and birds grew richer and more complex with Aeronis, weaving new connections between distant lineages and illustrating how the quest for the skies was a gradual, branching process rather than a single dramatic leap. Locomotor studies on Aeronis suggest a creature equally adept at life on the forest floor and brief forays into the air. Its hind limbs show adaptations for running and jumping, a long femur, elongated metatarsals, and a stiffened tail for counterbalance. Field experiments with digital models estimate that Aeronis could launch itself from low perches, extend its wings and tail feathers to generate lift, and glide up to 10 meters before landing. Such controlled descents would have offered escape routes from predators, efficient travel between feeding sites, and new vantage points for spotting prey. This dual locomotion strategy underscores the incremental evolution of flight, rooted in practical advantages long before sky-dominating prowess emerged. The paleo-environment of Aeronis was shaped by volcanic activity, lush mixed forests, and seasonally fluctuating climates. Coniferous trees and broadleaf ferns provided layered canopies teeming with insects, small reptiles and early mammals, while ashfall events preserved this diversity in stunning detail. In this dynamic ecosystem, Aeronis coexisted with giant thermophilic salamanders, gliding pterosaurs and small mammals, scampering across a mosaic of volcanic soils and freshwater lakes. Each ash layer captured a moment in this ancient world, immortalizing delicate feathers and bones in exquisite three-dimensional relief, snapshots of life's fleeting dances preserved for eternity. Dietary habits in Aeronis appear to have been opportunistic. Its slender, recurved teeth hint at an insectivorous diet supplemented by small vertebrates and possibly seeds or fruit. Wear patterns on fossil teeth suggest abrasive particles consistent with plant matter, while the jaw's swift closure points to rapid prey capture. This dietary flexibility would have been crucial in environments where prey availability fluctuated with volcanic winters and seasonal rainfall. In times of scarcity, Aeronis may have gleaned extra nutrients from seeds or consumed eggs and hatchlings of even smaller vertebrates, leveraging its agility and feathered limbs to explore niches inaccessible to bulkier predators. Behaviorally, social and reproductive strategies of Aeronis likely echoed those of early birds. Excavations have yet to uncover direct nesting sites, but the presence of multiple individuals in close proximity suggests communal roosting or foraging. During breeding seasons, males may have used contoured feathers on the head or throat for courtship displays, puffing out plumes to attract mates much like modern birds. Vocalizations, though elusive in the fossil record, could have accompanied these displays, creating a symphony of calls and rustling feathers at dawn. Such complex behaviors point to an emerging suite of social rituals that would come to define avian life. As dusk descended and ash, smoke mingled with mist, Aeronis would settle on a low branch, tucking its elongated feathers close against its body. It would ride the cooling evening breeze, flicking its tail plumes in subtle massages to deter parasites and adjust its thermal blanket. In the hush of prehistoric night, the faint rustle of feathers and the soft murmur of distant waters would envelop this tiny dawn bird, a creature suspended between reptile and avian realms. Though it never mastered powered flight, Aeronis embodied nature's restless experimentation, its legacy living on in every downy contour and every gliding silhouette that graces modern skies. Part 9. Archaeopteryx. In the ancient limestone lagoons of what is now southern Germany, some 150 million years ago, a creature took to the air that would forever alter our understanding of evolution. Archaeopteryx lithographica, a name that resonates through the annals of paleontology, represents one of the most iconic and hotly debated transitional fossils ever discovered. It possessed both the skeletal architecture of a theropod dinosaur and the aerodynamic features of a bird, blurring the line between the two worlds. With a wingspan of about half a meter and a weight similar to that of a modern pigeon, it glided silently above the shallow marine landscapes, its feathered wings catching the warm Jurassic breeze. This creature, preserved in slabs of Solnhofen limestone with such delicacy that even the imprint of its feathers remains visible, embodies a critical chapter in the story of avian origins. The skeleton of Archaeopteryx is a masterclass in evolutionary compromise. Its long bony tail, toothed jaws, and clawed fingers reflect its dinosaurian heritage, inherited from its close relatives among the dromaeosaurs and troodontids. Yet, the presence of asymmetric flight feathers on both its wings and tail, along with a wishbone known as a furcula, signals a distinct adaptation toward aerial movement. Its wings were powered by relatively strong pectoral muscles, and its shoulder girdle had begun to adapt for the upstroke and downstroke needed in flapping flight. While the sternum lacked the full keel found in modern birds, it provided a rudimentary base for muscle attachment. Each part of its skeleton reveals a mosaic of features, primitive and derived, that mark a crucial phase in the evolution of flight. The feathers of Archaeopteryx were intricately structured, indistinguishable in many ways from those of modern birds. Each wing boasted a full set of primary and secondary feathers, arranged to maximize lift and control. The feathers were asymmetrical, an essential characteristic of flight-worthy plumage, capable of supporting gliding or possibly powered flight. Along the tail, long veined feathers formed a rudder-like structure, aiding in stability and maneuverability mid-air. Even body feathers, though less specialized, suggest an insulating function, offering protection against the fluctuating temperatures of the Jurassic climate. These feathered adaptations underscore the fact that flight, or at least the capacity for aerial movement, evolved gradually and was tested through numerous evolutionary paths. The environment in which Archaeopteryx lived was unique, an archipelago of small islands, lagoons and tidal flats nestled in a shallow sea that covered much of present-day Europe. These islands provided the ideal setting for early flight experiments. Isolated trees and rocky outcrops offered launch points for glides, while open waters and soft sediments made for relatively safe landings. The presence of pterosaurs in the same ecosystem introduced aerial competition, though Archaeopteryx likely occupied a different ecological niche. It may have darted between tree branches or leapt from cliff sides, using its feathers for controlled descents or bursts of flapping to escape predators and search for food. The Solnhofen Formation, known for its fine-grained limestone, preserves this lost world in unparalleled detail, offering a rare glimpse into a time when both air and land were battlegrounds for evolutionary innovation. The diet of Archaeopteryx has long been the subject of debate, but current evidence supports a carnivorous lifestyle similar to its theropod ancestors. Sharp, recurved teeth line its upper and lower jaws, well suited for grasping and slicing soft-bodied prey, such as insects, small lizards or amphibians. Its claws, especially on the hands, may have aided in climbing or in subduing wriggling victims. Some theories propose that it may have hunted in short bursts, using surprise and agility rather than prolonged pursuit. Alternatively, it may have been an opportunistic feeder, gleaning morsels from tidal pools or scavenging from the remains of other creatures washed up along the shore. This flexible approach to feeding would have served it well in a landscape where food availability could fluctuate with tides and seasons. Locomotion in Archaeopteryx was a blend of terrestrial agility and limited flight. While it was capable of perching, Its foot structure suggests it was not as specialized for this behavior as modern birds. Instead, its curved claws and flexible joints hint at climbing ability, perhaps scaling tree trunks or rocky outcrops in search of food or refuge. On the ground, its legs, long and slender, allowed for quick bipedal movement, reminiscent of its dinosaurian cousins. In the air, studies of wing loading and feather structure suggest it was capable of flapping flight, though not with the sustained power of later avian forms. Its strength lay in short, controlled bursts, perfect for navigating the fragmented island habitats and avoiding the dangers that lurked below. Reproductive habits in Archaeopteryx remain speculative due to the lack of fossilized nests or eggs, but comparisons with both theropods and early birds provide clues. It likely laid eggs in simple ground nests or shallow scrapes, perhaps lined with plant material or feathers. Parental care, if it existed, may have been minimal or limited to guarding the nest, though the evolution of more intensive care would emerge in later avian lineages. Hatchlings were probably precocial, born with the ability to walk or even clamber soon after emerging from the egg, increasing their chances of survival in a world where predation pressures were ever present. This blend of ancient and emerging behaviors paints a picture of a species balancing its past and future with each generation. The discovery of Archaeopteryx in the 19th century marked a turning point in the study of evolution. Its unveiling shortly after Darwin's On the Origin of Species provided a tangible example of a transitional form, bridging the gap between reptiles and birds. Each subsequent fossil, of which over a dozen have been found, has added new detail to the portrait of this remarkable animal. From the famed Berlin specimen to more fragmentary remains, every bone and feather has contributed to a debate that continues to evolve with new technologies and discoveries. It challenges scientists to constantly re-examine definitions of what it means to be a bird, to fly, or to occupy the liminal space between two worlds. In quiet moments, with its feathers ruffling in the warm breeze of a Jurassic evening, Archaeopteryx would have stood still among the reeds, listening for the buzz of insects or the rustle of small animals. It was a creature of twilight, of transitions and thresholds, living at a time when the air was no longer ruled solely by reptiles and the future of birds had just begun to take shape. Its legacy lives on in every sparrow and hawk, its bones echoing in the beating wings of modern skies. In the hush of prehistoric silence, Archaeopteryx was neither fully dinosaur nor fully bird, but something breathtakingly in between. Part 10. Confucius ornis. In the early Cretaceous forests of what is now northeastern China, a small and elegant bird-like creature soared above the canopy, its long tail feathers streaming behind it. Confucius ornis stands out as one of the earliest known birds with a toothless beak, a significant evolutionary advancement. This avian lived approximately 125 million years ago and has been discovered in abundance within the fossil-rich layers of the Ixian Formation. The sheer number of well-preserved specimens offers a rare glimpse into the diversity and biology of early birds. These fossils show complete skeletons, soft tissue impressions, and remarkably detailed feather arrangements. As a transitional species, Confucius ornis bridges the gap between the ancient reptilian features of earlier avian forms and the more derived anatomy seen in modern birds. The body plan of Confucius ornis was a fascinating blend of the old and the new. It retained ancestral features like claws on its wings, yet showed clear signs of avian specialization with its beak and flight feathers. It was roughly the size of a modern pigeon, but its overall silhouette was elongated and slender. The feathers on its wings and tail were not only well developed, but also highly specialized, with some individuals displaying two long ribbon-like tail feathers believed to have been used for display rather than flight. This presence of sexual dimorphism suggests that visual communication, potentially for courtship, was already playing a role in these early avian communities. Some specimens exhibit these long ornamental feathers, while others do not, indicating possible differences between males and females, or even between juveniles and adults. Despite its avian characteristics, Confucius ornis lacked several features found in modern birds, particularly a keeled sternum. This structure in contemporary birds serves as an anchor point for powerful flight muscles, and its absence in Confucius ornis suggests that it wasn't capable of sustained powered flight. Instead, it likely relied on short bursts of flapping and gliding through dense forests. Its skeletal proportions hint at a lightweight body and strong forelimbs, which may have given it enough lift for leaping from branches and gliding to nearby perches. Such adaptations would have been ideal for a forested environment, where navigating through a complex network of trees required agility more than speed. Confucius ornis may have relied on a combination of jumping, flapping, and gliding, not unlike what is observed in some modern arboreal birds. The toothless beak of Confucius ornis is one of its most notable features, setting it apart from earlier avian ancestors like Archaeopteryx, which still possessed small, sharp teeth. The evolution of a beak in place of teeth marks an important divergence in avian development, both functionally and behaviorally. This keratinous beak may have allowed Confucius ornis to explore a wider variety of diets, potentially including seeds, fruits, or even small invertebrates. Although direct evidence of its diet remains limited, a few fossil specimens have been found with fish remnants near their ribcage, suggesting it may have consumed aquatic prey on occasion. The presence of a beak also points to the beginning of a major trend in bird evolution, one that favored lighter, more efficient skulls and feeding strategies. Its feet and claws were highly adapted for perching, a trait associated with life in trees. The toes were elongated and curved, with a reversed hallux, or first toe, a characteristic seen in perching birds. This arrangement would have allowed Confucius ornis to grasp branches securely, providing stability while navigating its arboreal environment. The presence of claws on its wings may have further aided in climbing or balancing along tree limbs. Some paleontologists suggest that Confucius ornis spent a significant portion of its life above ground, flitting through foliage and possibly nesting high in the treetops. Its lifestyle would have involved careful movements through a complex vertical world, where agility and balance were essential for survival, avoiding predators and searching for food. The extraordinary preservation of Confucius ornis fossils provides important information not just about its anatomy, but also its behavior and social patterns. Many specimens have been found clustered together, sometimes in groups of dozens. These groupings have led researchers to hypothesize that Confucius ornis may have been social, forming flocks or colonies. Group behavior could have offered protection from predators and improved success in finding food or mates. Additionally, the fossil sites where these clusters are found indicate rapid burial events, likely from sudden volcanic ash falls or mudslides, which preserved them in lifelike poses. These conditions have allowed paleontologists to study how these early birds may have interacted, traveled, and even died together. Coloration in Confucius ornis is a subject of increasing interest, thanks to recent advancements in the study of fossilized melanosomes, pigment-containing organelles found in feathers. Through microscopic analysis of these structures, scientists have begun to piece together the possible coloration of its plumage. While not every specimen yields enough data for precise reconstruction, some evidence points toward a range of dark hues, potentially blacks and reddish browns, with possible iridescent qualities. These pigments may have played roles in camouflage, thermoregulation, or visual signaling. The long tail feathers in some individuals likely had a visual function, hinting at courtship displays or species recognition, not unlike the tail feathers of modern peacocks or birds of paradise. Confuciusornis lived during a dynamic time in Earth's history, when many lineages of feathered dinosaurs and early birds were evolving in close proximity. The ecosystems of early Cretaceous China were biologically rich and geologically active, dominated by coniferous forests, lakes, and periodic volcanic eruptions. This volatile landscape was filled with predators like early troodontids and dromaeosaurs, as well as other avians and feathered theropods. Within this diverse environment, Confuciusornis carved out a niche as a small, agile, possibly omnivorous creature, perfectly suited to forested habitats. It likely competed with other feathered species for food and space, while avoiding both ground-dwelling and aerial predators. The interplay between competition, environmental pressures, and evolutionary innovation helped shape the course of its development and eventual extinction. Confuciusornis continues to captivate researchers due to its unique position in the evolutionary tree. It represents a pivotal stage where features characteristic of modern birds were beginning to emerge, but had not yet fully replaced the more primitive traits. With its toothless beak, feathered body, and possible social behavior, it reflects a complex organism adapting to a rapidly changing world. Each fossil adds new pieces to the puzzle, offering insight into not just this individual species but the broader story of avian evolution. The sheer volume of fossils and the depth of their preservation make Confuciusornis a key figure in the ongoing study of how dinosaurs gave rise to the vibrant and diverse clade of birds that inhabit the world today. Part 11. Jiaoholornis. In the ancient woodlands of what is now northeastern China, long before modern birds filled the skies, a strikingly primitive yet remarkably bird-like creature moved through the treetops. This was Jiaoholornis, an early avian that lived around 120 to 125 million years ago during the early Cretaceous period. Its name translates to Jiahol bird, derived from the region where it was discovered, and it stands out as one of the longest-tailed birds ever known. Unlike modern birds, which have short pygo-style supported tails, Jiaoholornis retained a long, bony tail comprised of over 20 vertebrae, more akin to its dinosaur ancestors than contemporary avians. This unusual combination of traits has made Jiaoholornis one of the most fascinating transitional species, bridging the evolutionary gap between non-avian dinosaurs and birds. The body of Jiaoholornis was a blend of old and new anatomical elements, highlighting its position near the base of the avian evolutionary tree. Its arms were long and ended in three-fingered hands with claws, a feature inherited from its theropod ancestors. Though it possessed feathers suited for flight, its capabilities in the air remain a matter of scientific debate. Some paleontologists suggest that Jiaoholornis may have been capable of limited powered flight, while others believe it was primarily a glider, using its wings to extend leaps between trees. Its long tail, adorned with feathers along its length, and a distinctive fan at the tip, may have served both for balance during arboreal movement and as a stabilizer during flight. The dual functionality of its tail underscores how evolution often repurposes traits across different contexts. The beak of Jiaoholornis was another key trait, completely lacking teeth at the front and narrowing into a pointed structure. However, the back of its jaws still retained a few small teeth, giving it a mixed dental profile not seen in modern birds. This intermediate condition hints at a dietary shift in progress, from a fully carnivorous lifestyle to a more herbivorous or omnivorous one. Fossil evidence has shown that Jeholornis likely fed on fruits and seeds, with some preserved specimens even containing whole seeds within the body cavity. This dietary specialization suggests that early birds like Jeholornis were beginning to exploit ecological niches unavailable to their fully carnivorous ancestors, including new sources of plant-based food that may have helped them survive in changing environments. The Jehol biota, the fossil-rich ecosystem from which Jeholornis hails, provides a vivid backdrop for its existence. This ancient environment was marked by temperate forests, lakes, and volcanic activity, which helped preserve countless organisms in extraordinary detail. These surroundings were home to a wide range of feathered dinosaurs, primitive mammals, early amphibians, and flowering plants. Among these ancient ecosystems, Jeholornis likely shared the canopy with relatives such as Confuciusornis and Sapornis, as well as predators like Microraptor. Its arboreal adaptations, including curved claws for grasping branches and strong hind limbs, suggest it spent much of its time moving among the trees. The evolutionary pressures in such a biodiverse setting likely pushed Jeholornis toward enhanced maneuverability, dietary versatility, and sensory development. The plumage of Jeholornis tells another part of its story. Fossils reveal well-developed feathers on its arms and tail, but none on its legs or lower body, an unusual distribution that suggests a transitional state in feather evolution. The long, ribbon-like tail feathers were symmetrical and likely played a role in flight stability or visual display. While melanosome analysis, the study of pigment-bearing organelles in fossilized feathers, is still in its infancy for this species, there's some indication that the plumage may have been patterned or lightly colored. If so, Jeholornis could have used its feathers for communication, camouflage, or mate attraction. The evolution of feathers in this species reflects their gradual shift from insulation and display to more complex roles in flight and behavior. The skeleton of Jeholornis offers key clues into its evolutionary status. Though superficially bird-like, it retained many basal features. Its pelvis, for instance, was still more similar to non-avian theropods than modern birds, and it lacked a fully developed keel on its sternum, the structure that in modern birds supports large flight muscles. This suggests that while Jeholornis was feathered and possibly capable of gliding or short bursts of flight, it had not yet developed the anatomical refinements necessary for long-distance or highly agile flying. Its flight capability likely resembled that of a modern flying squirrel, more than that of a sparrow or swallow, more about navigating the spaces between trees than crossing open skies. One of the most compelling aspects of Jeholornis is its role in the narrative of avian evolution. As an early bird with primitive skeletal traits and a modern-style beak, it represents a clear step in the transformation from ground-dwelling theropods to flight-capable birds. Unlike Archaeopteryx, which still bore a full set of teeth and a less bird-like skull, Jeholornis marks a progression toward modern bird morphology. Its existence underscores that avian evolution was not linear, but filled with experimentation. Different species evolved feathers, beaks, and flight in various combinations, some of which proved successful while others faded into extinction. Jeholornis, with its peculiar anatomy, was part of this evolutionary branching, carving out a temporary but meaningful niche. Interestingly, the population of Jeholornis seems to have been relatively widespread within the Jehol ecosystem, as indicated by the large number of well-preserved specimens. The preservation quality of these fossils allows researchers to study not just its bones but also details like stomach contents, feather arrangements, and even pathologies. Some individuals show healed injuries, suggesting they lived long enough to recover from trauma, indicating a degree of resilience in their lives. Others are found with seeds in their crops, offering direct insight into feeding habits and digestion. These intimate glimpses make Jeholornis not just a fossil curiosity, but a living, breathing animal with its own behavioral ecology, shaped by its environment and evolutionary pressures. The legacy of Jeholornis continues to influence the scientific understanding of how birds emerged from their dinosaurian ancestors. It provides a critical data point in reconstructing the timeline and sequence of avian evolution. By examining its mix of modern and ancestral features, scientists can piece together how and when traits like beaks, feathers, flight, and dietary shifts emerged. Jeholornis didn't survive into the modern age, but its contribution to the lineage that did is unmistakable. Its fossils serve as a bridge to a time when birds were still finding their shape, and every new discovery continues to shed light on the incredible journey from dinosaurs to birds. Its story is not just one of feathers and fossils, but of the slow, steady crafting of flight and form over deep time. Part 12. Rohonovis. Among the fascinating patchwork of feathered dinosaurs and early birds, Rohonovis stands out as a mysterious and enigmatic creature. Discovered in the late Cretaceous deposits of Madagascar, this small dinosaur lived around 70 million years ago, toward the end of the Mesozoic era. Its name means cloud menace, hinting at both its lightweight, potentially aerial lifestyle and the mystery that still surrounds it. Rohonovis possessed an intriguing combination of avian and theropod features, blending elements that are typically associated with both flight-capable birds and their ground-dwelling ancestors. This complex mosaic has led to continued debate among paleontologists about its classification, whether it was an early bird, a close bird relative, or something more uniquely placed on the evolutionary tree. The skeleton of Rohonovis was small, with an estimated body length of less than 1 meter. Despite its modest size, the animal had an unusually robust and specialized anatomy. One of its most notable features was a large sickle-shaped claw on its second toe, similar to the infamous dromaeosaurid raptor claw seen in Velociraptor. This claw was likely used for hunting or climbing, and indicates that Rohonovis retained strong predatory instincts, even if it had some capability for flight. The claw also suggests that Rohonovis may have had behaviors more akin to agile land hunters than the tree-perching or seed-foraging lifestyles imagined for other bird-like dinosaurs. This blending of traits paints a picture of a creature that could adapt to multiple niches, perhaps able to pursue prey on the ground and retreat to higher places when needed. Another fascinating aspect of Rohonovis is its forelimbs. Fossil analysis reveals that it had long, well-developed arms and a shoulder girdle structured in a way that would allow for a wide range of motion. These characteristics are commonly associated with flight-capable animals. Its ulnar and radius bones, parts of the forearm, were curved and strong, and there was evidence of quill knobs, the bony attachments for large flight feathers. This indicates that Rohonovis likely had substantial feathers suited for either gliding or powered flight. However, whether it could truly fly like a modern bird is still debated. Some scientists believe Rohonovis had a rudimentary flapping flight ability, perhaps akin to that of pheasants or other birds that rely on short bursts of flight rather than sustained soaring. Others argue it was a ground-dwelling predator that only used its wings for balance or threat displays. The pelvis and hind limbs of Rohonovis also tell a story of hybrid features. Its hips retained characteristics common to non-avian theropods, while the structure of its legs hints at an agile bipedal locomotion. Strong thighs and flexible ankle joints suggest it could run quickly across the ground, chasing prey or evading larger predators. The proportions of its legs imply it may have spent significant time on the ground, using its feet to grapple, dig, or manipulate objects. This would align with its dromaeosaurid relatives, known for their terrestrial hunting prowess. If Rhohornivus did have the ability to fly, it may have been in short bursts, as a supplement to its fast and nimble life on the forest floor or through thick vegetation, rather than as a primary mode of travel. Rhohornivus lived in what is now Madagascar, a region that during the late Cretaceous was teeming with life and somewhat isolated from other landmasses. This isolation may have played a role in the animal's unique mix of features. With limited competition or interaction from other dinosaur faunas, evolutionary pressures could have carved out distinct forms like Rhohornivus that blended flight adaptations with land-based predatory traits. The ancient ecosystems of Madagascar included towering conifers, flowering plants, and a host of other dinosaurs, some of which are still poorly understood. Rhohornivus may have filled a niche similar to that of a small predatory bird of prey today, stalking insects, small reptiles, and even mammals among the underbrush, or swooping from low branches for a quick strike. The plumage of Rhohornivus remains somewhat speculative due to the limited fossil material, but based on its close relatives and the evidence of feather attachment points, it almost certainly had a feathered body. These feathers may have varied in form, downy for insulation, longer and more rigid for flight or display, and patterned for camouflage or communication. In the dense foliage of Cretaceous Madagascar, feathers could have offered multiple advantages, not just flight, but warmth during cooler nights, visual signals to mates or rivals, or concealment from predators. The presence of feathers in a dinosaur with such a pronounced killing claw also offers a striking image, an animal both deadly and delicate, armored in plumage yet built to hunt. One of the challenges in studying Rhohornivus is the fragmentary nature of its fossils. The primary specimen found in the Maverano Formation is incomplete, making it difficult to resolve its exact evolutionary relationships. Some features place it within the dromaeosaurids, while others suggest avian affinities, possibly placing it just outside the group that includes all modern birds. This ambiguity highlights the blurred lines in the evolutionary transition from dinosaurs to birds. Creatures like Rhohornivus emphasize that evolution does not operate in a neat, linear path. Instead, it produces a wide array of experimental forms, some of which possess a perplexing mix of traits that don't fit comfortably into the categories humans like to use. The study of Rhohornivus has also fueled discussions around convergent evolution and mosaicism in the fossil record. It stands as a reminder that flight and bird-like characteristics evolved multiple times and in varied ways among theropods. Whether Rhohornivus represents an independent flight experiment or an offshoot of an early bird lineage, it broadens the understanding of how versatile and adaptive these creatures were. It also reinforces the notion that feathered dinosaurs were not confined to a singular evolutionary story. Instead, they branched off into diverse and complex forms, each shaped by their environment and lifestyle demands. The uncertainty around Rhohornivus is not a limitation, but rather a point of excitement for researchers seeking to unlock the secrets of deep time. Ultimately, Rhohornivus adds a vital chapter to the unfolding narrative of flight and bird evolution. Its combination of terrestrial agility and avian traits exemplifies the dynamic range of life that existed during the Cretaceous, challenging assumptions about what makes a bird and what remains purely dinosaur. With further fossil discoveries and advanced imaging techniques, more details about its life and behavior may come to light. Until then, it serves as a symbol of evolutionary creativity, a creature not quite bird, not fully raptor, but undeniably remarkable in its own right. Its legacy lies in the questions it raises, the mysteries it deepens, and the evolutionary links it so beautifully illustrates between the skies above and the ancient forests below. Part 13. Troodon. In the late Cretaceous period, roughly 76 to 70 million years ago, a small yet remarkably advanced dinosaur moved through the dense forests and floodplains of what is now North America. This was Troodon, a genus that has intrigued paleontologists since the first tooth was discovered in the 19th century. The name Troodon translates to wounding tooth, and even its dentition was unusual, serrated and recurved with a shape that hinted at a potentially omnivorous diet. Unlike many other theropods of its time, Troodon was lightly built, with a long, slender tail, nimble legs, and a body that stretched around 2.5 meters in length. It likely weighed just over 40 kilograms, making it relatively small but extremely agile. Its skeletal structure suggests speed and precision, traits that would have been key to thriving in a competitive ecosystem full of predators, prey, and constant environmental shifts. One of the most fascinating aspects of Troodon is its brain-to-body ratio, which remains among the highest known for any non-avian dinosaur. The enlarged brain case suggests a level of neurological development that far exceeded that of most of its contemporaries. Paleontologists have long speculated that this may have endowed Troodon with heightened sensory perception, especially when it came to sight and possibly hearing. Its forward-facing eyes were large, granting it the gift of binocular vision and exceptional depth perception, traits crucial for a predator that may have stalked or ambushed its prey. Some researchers suggest Troodon might have been nocturnal, given the relative size of its eyes, which would align with a hunting strategy favoring low-light environments like twilight forests or moonlit plains. These anatomical clues come together to paint a portrait of a creature that was not just reactive to its surroundings, but proactively engaged with them in complex ways. Equally intriguing is the structure of Troodon's teeth. With serrations more akin to those of herbivores than traditional carnivores, it's likely that this dinosaur had an omnivorous diet. It may have dined on small vertebrates, insects, eggs, and even certain types of plants. This flexibility in diet would have been a significant advantage in a prehistoric world, where survival often depended on adaptability. The potential for omnivory places Troodon in a unique ecological niche, capable of thriving in multiple environments and seasons. This dietary versatility could help explain why Troodon fossils have been discovered across such a wide range of locations in North America, from the chilly regions of Alaska to the arid badlands of Montana and Alberta. Its ability to exploit a range of food sources might have allowed it to outlast or outmaneuver more specialized species that shared its environment. Troodon's reproductive habits provide yet another layer of interest. Fossilized nests associated with this genus show well-organized arrangements of eggs, suggesting deliberate and intelligent nesting behavior. The eggs were often found in pairs, indicating that Troodon had two functional oviducts, like modern reptiles and unlike birds, which have only one. Some fossil sites have even preserved adult remains close to the nests, leading to speculation about potential parental care, an extremely rare trait among non-avian dinosaurs. The idea that Troodon may have guarded its young or maintained the nest's temperature through brooding is an evocative glimpse into its behavioral complexity. These nesting behaviors, paired with its intelligence and agility, suggest a dinosaur that was as much a caretaker as it was a hunter, adding depth to our understanding of its daily life and reproductive strategies. The taxonomic history of Troodon is complex and still evolving. Originally described based on a single tooth, Trudon became a sort of catch-all category for a variety of similar small theropod fossils. This led to decades of confusion, with numerous species being lumped together under the Trudon umbrella. Over time, paleontologists began to differentiate between these specimens, leading to new genera like Stenonychosaurus and Latinivnatrix being split off from the Trudon genus. Despite the reclassification, the name Trudon has endured in popular culture and scientific literature as a symbol of the intelligent, bird-like theropods that challenged traditional views of dinosaurs as slow, dim-witted reptiles. Today, debates continue about which fossils truly belong to Trudon and whether the name itself will remain in use in the future. One of the most compelling what-ifs in paleontology involves Trudon and its potential evolutionary path. Some scientists have speculated that, had the mass extinction event at the end of the Cretaceous not occurred, Trudon or its relatives might have continued to evolve into even more intelligent forms. This idea gave rise to the speculative concept of the dinosauroid, a hypothetical dinosaur with a large brain, upright posture, and even manipulative hands, not unlike a humanoid. While such scenarios remain purely hypothetical, they highlight the fascination Trudon holds in both scientific circles and the public imagination. Its anatomy opens a window into what intelligence may have looked like in a lineage far removed from primates. The geographic range of Trudon adds another layer of intrigue. Fossils attributed to this genus have been found from the Arctic Circle down to more temperate latitudes, indicating an extraordinary capacity for environmental adaptation. In the high latitudes of Alaska, Trudon may have faced extended periods of darkness and cold temperatures. Its survival in such harsh climates suggests that it may have possessed some degree of endothermy or warm-bloodedness, a trait also proposed for many other theropods. This potential for thermoregulation would have allowed it to maintain activity levels even during cold seasons, providing yet another advantage over more reptilian competitors. If true, this could mark Trudon as one of the more advanced examples of dinosaur physiology in its time. Interestingly, the anatomy of Trudon's limbs and claws also supports the notion of a highly dexterous and intelligent animal. Its hands had 3 fingers, one of which was partially opposable, giving it a potential for grasping and manipulating objects. While this does not imply tool use in the modern sense, it does indicate a capability for complex interactions with its environment, whether for hunting, foraging, or even nesting. The sickle-shaped claw on its second toe, a feature shared with other trudontids and dromaeosaurs, might have served multiple purposes, from dispatching prey to climbing or digging. These versatile appendages further underscore how Trudon stood apart from many of its dinosaurian peers in both form and function. Ultimately, Trudon remains one of the most enigmatic and thought-provoking dinosaurs discovered to date. Its blend of anatomical sophistication, behavioral complexity, and ecological versatility challenges the traditional image of dinosaurs and nudges paleontology toward new understandings of ancient life. While some aspects of its classification may remain in flux, Trudon continues to inspire questions about intelligence, adaptability, and what it truly meant to be a dinosaur in the age before birds fully took to the skies. Whether viewed through the lens of hard science or imaginative speculation, Trudon holds a unique and enduring place in the ever-expanding story of Earth's prehistoric past. Part 14. Protarchaeopteryx. Protarchaeopteryx, a name that means before Archaeopteryx, offers an intriguing puzzle in the story of feathered dinosaurs. Despite its name suggesting it predates Archaeopteryx, it actually lived millions of years later during the early Cretaceous period, around 124 million years ago, in what is now northeastern China. This small dinosaur measured just under a meter in length, with a body about the size of a modern-day turkey. What makes Archaeopteryx especially fascinating is the way it embodies both primitive and advanced traits, features that tie it to more ancient theropods, while also hinting at its connections to birds. Fossils discovered in the rich beds of the Ixian Formation have preserved fine details of this creature's body, including evidence of plumage, offering a valuable look into a critical stage in the evolution of feathers and feathered dinosaurs. The feathers of Archaeopteryx are among its most remarkable traits. They were symmetrical, simple veined feathers, far less complex than those of modern birds, and not suited for flight. Instead of being adapted for aerial movement, these feathers were likely used for other purposes, such as insulation, camouflage, or even display during social interactions. Long tail feathers, arranged in a fan-like pattern, suggest the possibility of mating displays or territorial signaling, much like how some modern birds use their tail plumage. The feathers on its arms may have added to this visual display or helped it regulate body temperature. These traits show that feathers likely evolved for reasons other than flight, only later becoming adapted for lift and gliding in other species. The skeletal anatomy of Archaeopteryx further adds to its evolutionary importance. It had long legs that indicate it was a fast runner, capable of darting quickly across the forest floor. Its arms were long and slender, ending in three-fingered hands with curved claws, useful for grasping or manipulating objects. The presence of a wishbone, or furcula, along with hollow bones, connects it anatomically to birds. Yet it also retained a number of more primitive features, including a long bony tail and relatively simple teeth. This mix of traits places Archaeopteryx as a bridge between non-avian dinosaurs and birds, not as a direct ancestor, but as a cousin, showing what evolutionary experimentation looked like at the time. Dietary clues in Archaeopteryx's anatomy suggest it was an omnivore. Its teeth were small and peg-like, suited for nipping at vegetation or catching small invertebrates. It may have foraged on the ground for seeds, fruit, or insects, using its keen vision and agile hands to pick through leaf litter or low vegetation. The flexibility of its diet would have been a key to its survival, especially in a dynamic environment like that of early Cretaceous China. Such adaptability might have given it an edge in the complex ecosystems it inhabited, where competition for resources could have been intense among the numerous feathered species sharing its habitat. The Ixian Formation, where Archaeopteryx was found, is one of the most important fossil sites in the world for understanding feathered dinosaurs. The volcanic ash and fine sediments preserved soft tissues, feathers, and even pigmentation patterns with astonishing detail. Archaeopteryx lived among an incredible variety of creatures: early mammals, amphibians, reptiles, flowering plants, and many other feathered dinosaurs, including close relatives like Archaeopteryx and Sinosauropteryx. These ecosystems were vibrant and complex, with lakes, forests, and frequent volcanic eruptions shaping the landscape. In this setting, Archaeopteryx played a role in the ever-evolving dance of predator and prey, adaptation and survival. Comparisons between Archaeopteryx and more advanced oviraptorosaurs reveal the stepwise development of traits that would eventually characterize modern birds. Although it is one of the more basal members of the oviraptorosaur group, Archaeopteryx already displayed several evolutionary innovations. These include a shortened snout, a high tooth count, and the presence of elongated tail feathers. Over time, later oviraptorosaurs would lose their teeth entirely, develop beaks, and adopt more complex nesting behaviors. Archaeopteryx stands at the beginning of this lineage, retaining enough primitive traits to show its ancestry while beginning to explore new evolutionary directions. There's something visually striking about Archaeopteryx's long tail, adorned with a fan of feathers. The structure would have been light but stiff, ideal for maintaining balance while running or maneuvering through underbrush. In modern birds, tail feathers are essential for steering in flight, but for a grounded creature like Archaeopteryx, their purpose may have been entirely different. Perhaps it fanned its tail feathers during threat displays or used them to appear larger in the presence of predators. The development of such a dramatic tail feature illustrates how feathers could have had multiple functions before being co-opted for aerial navigation. Studies on Archaeopteryx have sparked discussions on the multiple origins and functions of feathers within the dinosaur lineage. Not all feathers evolved with the purpose of flight, and Archaeopteryx provides a clear example of this. Its feathers could represent an early stage in feather evolution, where function revolved around display or thermoregulation. This adds nuance to our understanding of how flight evolved, not in a single leap, but through a series of adaptations that included traits like feather length, symmetry, and bone structure. These piecemeal developments eventually coalesced into flight-capable lineages, but for Archaeopteryx, staying grounded was just part of its ecological niche. Archaeopteryx's role in paleontology goes beyond its specific traits. It serves as a key representative of a period when feathered dinosaurs were diversifying in form, behavior, and habitat. The early Cretaceous was a time of great innovation, and Archaeopteryx exemplifies the experimentation in design and function occurring within the theropod lineage. It didn't take to the skies, but its feathered body shows that evolution was laying down the blueprint. Every fossil adds a new brushstroke to the canvas of prehistory, and Archaeopteryx is a vivid example of nature's creativity at work, bridging worlds, not with wings, but with feathers that hinted at what was to come. Part 15. Eosinopteryx. Eosinopteryx, a small feathered dinosaur from the late Jurassic period, challenges many long-held assumptions about the evolution of flight. Discovered in the fossil-rich rocks of northeastern China, this species was uncovered in the Tiaojisha Formation and dated to around 160 million years ago. Measuring just about 30 centimeters in length, it was a lightweight creature, roughly the size of a modern pigeon. Despite its diminutive stature, Eosinopteryx holds an important position in the study of feathered theropods, particularly those that were close to the avian lineage. Its fossilized remains are remarkably well preserved, revealing details about its feathers, bone structure, and overall body plan, offering valuable insights into how early feathered dinosaurs functioned and interacted with their environment. One of the most intriguing aspects of Eosinopteryx is that, although it possessed feathers, it likely was not capable of powered flight. Unlike modern birds or even some of its contemporaries like Archaeopteryx, Eosinopteryx lacked several crucial adaptations for flight. Its feathers were relatively short and unstructured for generating lift, and its forelimbs were not particularly long or robust, limiting the potential for wing beats. Additionally, its tail was short and lacked the stiffening adaptations seen in flying species, which would have been important for steering in the air. These anatomical limitations suggest that Eosinopteryx was a ground-dwelling or tree-climbing dinosaur, whose feathers served alternative functions unrelated to flight. The body plan of Eosinopteryx appears to be finely tuned for terrestrial agility. Its hind limbs were long and slender, likely allowing for quick bursts of speed across the forest floor. The toes were not particularly curved, indicating it wasn't strongly adapted for perching in trees like some of its later avian relatives. Meanwhile, The tail was proportionally short and not stiffened with long feathers, features that contrast with other feathered dinosaurs that were either experimenting with gliding or already capable of rudimentary flight. This terrestrial specialization paints a picture of a small, nimble creature darting between ferns and trees, hunting insects or small prey, and possibly using its plumage for signaling or thermoregulation. Feathers on Eosinopteryx's body were found covering much of its limbs and tail, though they appeared relatively simple in structure. The lack of asymmetry in the feathers, a feature important for flight, suggests that these were not meant for flying but instead for other evolutionary functions. Feathers can serve a variety of roles: thermal insulation, display, camouflage, or even brooding behaviors. For a small creature like Eosinopteryx, staying warm in cooler climates would have been essential, and feathers would have provided excellent insulation. The presence of feathering also supports the idea that feathers originally evolved not for flight, but for other survival functions, only later being adapted for aerial use. The discovery of Eosinopteryx also adds to the growing evidence that feathered dinosaurs were much more diverse in form and function than previously believed. In earlier interpretations of dinosaur evolution, feathers were mainly associated with flying or pre-avian species, but Eosinopteryx demonstrates that feathers were already widespread among small theropods, and they didn't necessarily signal a direct line toward flight. Instead, feathered species occupied a wide range of ecological roles. Some were climbers, some runners, and others potentially gliders or flyers. Eosinopteryx, grounded and agile, represents a variation within this feathered experiment, revealing the diversity of body plans that existed among early Microraptoran dinosaurs. In terms of evolutionary relationships, Eosinopteryx is believed to be a basal troodontid, or possibly closely related to the Anchiornithidae, a family of small feathered theropods with avian-like features. These groups are particularly interesting because they represent transitional forms in the dinosaur-to-bird narrative. Troodontids are notable for their large brains and advanced sensory abilities, and Eosinopteryx might have shared some of these traits. The positioning of this species within the evolutionary tree is still a matter of debate, but its existence helps illustrate how blurred the lines were between bird-like dinosaurs and non-avian dinosaurs during the Jurassic period. The habitat of Eosinopteryx was likely a subtropical forested environment filled with a wide range of life. The Teogestion Formation has yielded fossils of early mammals, amphibians, reptiles, insects, and numerous other feathered dinosaurs, suggesting a lush, vibrant ecosystem. Volcanic activity in the region may have contributed to the remarkable fossil preservation, capturing fine details of feathers and soft tissue. In such a complex and dynamic environment, Eosinopteryx would have faced constant pressures from predators, climate fluctuations, and competition for food, all of which could have shaped the evolutionary adaptations seen in its anatomy and behavior. The short tail and reduced plumage of Eosinopteryx have sparked particular interest among paleontologists, who see in them a counterpoint to the common narrative of increasingly bird-like dinosaurs during the Jurassic. Rather than following a straight path toward flight, Eosinopteryx seems to have taken a detour, a separate experiment in the utility of feathers and body design. It's possible that flight-capable ancestors may have existed, and species like Eosinopteryx adapted secondarily to a flightless, ground-based lifestyle, much like modern flightless birds such as ostriches and kiwis. This possibility adds depth to the evolutionary tree and complicates the simplistic view of one-directional progress toward flight. What Eosinopteryx ultimately represents is a snapshot in time, an example of the experimentation and variety that characterized the feathered theropods of the Jurassic. Its small size, modest feathering and grounded lifestyle show that nature was not rigidly aiming toward the skies, but was instead exploring a rich array of forms and functions. Every new fossil discovery like this one reveals the unexpected twists and turns of evolutionary history, suggesting that the path to birds as we know them was filled with side roads and unique adaptations. Eosinopteryx may never have soared through the air, but its evolutionary tale still carries great weight in understanding how feathers form and function co-evolved over millions of years. Part 16. Coelindrodromeus. Coelindrodromeus abicalicus was a truly groundbreaking discovery in the world of paleontology, revealing unexpected details about the evolution of feathers and challenging long-held ideas about which dinosaurs might have been covered in them. Found in the Jurassic Age rocks of southeastern Siberia, this small ornithischian dinosaur rewrote the rules. Unlike the feathered theropods discovered earlier, which belonged to the lineage that led to birds, Coelindrodromeus belonged to a completely different branch of the dinosaur family tree. That meant feathers might not have been limited to one group, but could have been a common feature for many, if not most, dinosaurs. This idea stirred considerable excitement, opening up new possibilities for understanding what ancient dinosaurs might have looked like. The fossil site where Coelindrodromeus was found was a Lagerstätte, an exceptionally well-preserved deposit that included not just bones but soft tissues and impressions of skin and filaments. The level of preservation was astonishing. Several specimens were uncovered, each one offering a clearer picture of how this dinosaur looked in life. Coelindrodromeus was small, bipedal, and herbivorous, standing about 1.5 meters long. Its body showed a fascinating combination of scales and feather-like filaments. It had typical reptilian scales on its tail and lower legs, but the rest of its body was adorned with 3 different types of filamentous structures. These ranged from simple hair-like filaments to more complex branched structures that resembled primitive feathers, although they were likely not used for flight. The presence of feather-like structures in a non-theropod dinosaur hinted at an ancient origin for feathers, possibly as far back as the common ancestor of all dinosaurs. That pushes the evolutionary timeline for feather development back significantly, indicating that feathers may have first evolved not for flight, but for other purposes such as insulation, display, or even sensory functions. The complex arrangement of these filaments suggests that the development of feathers was not linear or straightforward, but a messy branching process that evolved under different environmental and evolutionary pressures across many dinosaur lineages. This shifts the focus away from birds as the sole inheritors of feathers, showing instead that feathers were likely more widespread than once thought. Coelindrodromeus itself was built for agility. Its legs were long and strong, suitable for quick movement through its environment, which was likely a warm, forested habitat filled with ferns, cycads, and other Jurassic flora. Its skull was small with a beak-like snout, useful for cropping vegetation. Unlike many of the carnivorous feathered dinosaurs previously discovered, Coelindrodromeus was a dedicated plant eater. Its discovery balanced the view that feathers were a trait exclusive to fast, warm-blooded predators, showing that even slow-moving herbivores could sport them. This alone made Coelindrodromeus a standout discovery, changing our mental image of dinosaurs as solely scaly, reptilian creatures. The implications of this find went even further, sparking renewed debate among scientists about the definition and function of feathers in non-avian dinosaurs. Were these filaments true feathers, or a parallel evolutionary development? Could they be homologous to bird feathers, sharing a common origin, or were they analogous, similar in appearance and function but independently evolved. Researchers compared the fossil structures to both modern bird feathers and earlier feathered dinosaur fossils, examining their arrangement, texture, and microscopic details. While the answer remains debated, many experts lean toward the idea that these structures shared a common evolutionary origin with feathers, strengthening the hypothesis that feathers evolved before the rise of birds. The Coelendrodromeus specimens also showed that feather-like filaments could coexist with scales in a single individual. This mix of integument types supports the idea that dinosaurs had a wide variety of body coverings, far more diverse than previously imagined. The simple dichotomy of feathers or scales no longer applied. Instead, dinosaurs could display a mosaic of textures, with different body parts adapted for different functions: scales for protection and durability, filaments for insulation or communication. This level of complexity is more in line with what we see in modern birds and mammals, where skin coverings serve multiple roles and evolve in nuanced ways. The environment where Coelendrodromeus lived was also key to its preservation and the clues it provided. The fossil site in the Zabaikal region of Russia was once a lush wetland near volcanic activity, which helped rapidly bury the animals and preserve delicate features. The layers of volcanic ash that covered the dinosaurs may have sealed them in a near-perfect time capsule, preserving soft tissues that rarely survive the fossilization process. It is this context that allows paleontologists to study features that are usually lost to time. In doing so, it opens up a clearer window into what early dinosaurs looked like and how they lived. The discovery of Coelendrodromeus also encouraged scientists to revisit older fossils with new eyes. If feathers or feather-like filaments were present in a dinosaur as distantly related to birds as Coelendrodromeus, then it became plausible that other previously overlooked species might have had them as well. Some paleontologists began re-examining specimens from Europe, Africa, and North America, looking for traces of similar structures. This dinosaur sparked a wave of reanalysis and reinterpretation in museums and labs around the world, urging scientists to question assumptions and look more carefully at fossilized skin impressions and fine details in ancient bones. Coelendrodromeus serves as a powerful reminder of how a single discovery can ripple outward, reshaping an entire field of study. It broadened the scope of feather research and gave rise to new hypotheses about the function and origin of these evolutionary marvels. Rather than being a simple step on the path to flight, feathers may have evolved as a flexible and multifunctional adaptation used by many kinds of dinosaurs for a range of purposes. In life, Coelendrodromeus might not have soared through the skies, but it carried on its body the genetic and anatomical blueprint that millions of years later would lift birds into the air. Its story bridges ancient worlds and modern understanding, leaving behind a legacy that still stirs curiosity in the bones and filaments it left behind. Part 17. Sauromimus. In the rich limestone beds of Bavaria, Germany, a small but astonishing dinosaur fossil was discovered that would challenge long-held ideas about the evolution of feathers. This fossil belonged to Sauromimus albus duoferi, a juvenile theropod from the late Jurassic period, about 150 million years ago. Its name, which translates to squirrel mimic, was inspired by the strikingly bushy appearance of its tail, which, thanks to remarkable preservation, revealed evidence of filamentous structures resembling primitive feathers. This rare and exquisitely detailed fossil offered an unprecedented glimpse into the diversity of feathered theropods, far beyond the bird-like dinosaurs typically associated with plumage. Unlike the more famous feathered species discovered in China, Sauromimus was found in Europe, expanding the known geographic range of feathered non-avian dinosaurs. The fossil, discovered near Painton in southern Germany, came from the Torlater Formation, a geological layer known for preserving fine details of prehistoric organisms. The specimen was extraordinarily well preserved, capturing not just bones but also soft tissues and fine integumentary structures. These filamentous structures were found along the tail, back, and portions of the body, suggesting that this dinosaur was covered in a coat of primitive feathers. What made this discovery especially groundbreaking was that Cearumimus was not closely related to birds, yet it still displayed clear signs of feather-like covering. This hinted at a broader evolutionary trend, suggesting that feathers were not exclusive to the ancestors of birds, but may have been a common trait among a wider array of theropods. This evidence supports the increasingly accepted theory that feathers likely evolved before flight and may have had functions unrelated to aerial locomotion. Feathers in early theropods like Cearumimus could have served a variety of purposes, such as insulation to retain body heat, camouflage for hiding from predators or stalking prey, or even for display during social or mating rituals. The existence of such structures in a basal theropod suggests that the genetic and developmental basis for feather growth was already in place long before birds took to the skies. Rather than being a novel adaptation exclusive to avian lineages, feathers might have deep evolutionary roots stretching across the entire theropod family tree. Anatomically, Cearumimus exhibited several features typical of juvenile theropods. The proportions of its body, such as its large eyes, relatively short limbs and delicate skeletal frame, indicated that this individual was young at the time of death. Its skull was long and shallow, housing small, conical teeth that lacked the serrated edges found in many predatory dinosaurs. These features suggest that Cearumimus likely fed on small prey items such as insects or tiny vertebrates, which would have been appropriate for its size and age. Juvenile theropods often had different ecological roles compared to adults, and fossils like this one help scientists piece together the complex life cycles of dinosaurs. The classification of Cearumimus has sparked considerable debate among paleontologists. When first described, it was thought to belong to a group known as Megalosauridae, which are considered more primitive members of the theropod lineage. However, later research has placed it closer to the Coelurosaurs, a group that includes more bird-like dinosaurs. This shifting classification reflects the challenges in analyzing young specimens whose bones have not yet fully developed the characteristics used to identify adult dinosaurs. Nevertheless, its presence within the broader theropod group reinforces the notion that feather-like structures may have been far more common than once believed, even among groups not previously associated with such features. Another fascinating aspect of the Cearumimus fossil is the way it preserves early evidence of what might be called proto-feathers. Unlike the complex, branching feathers seen in later avian dinosaurs, these filaments were simpler in structure, more like hair or fuzz, than the aerodynamic feathers used for flight. This simplicity has led researchers to believe that the first feathers were not adapted for flying, but rather served entirely different roles. The soft, downy covering found on Cearumimus may have provided warmth or sensory functions, or even helped juveniles survive in cooler microclimates. This discovery has sparked comparisons with other theropods showing similar plumage, prompting a re-evaluation of how and why feathers developed in the first place. The limestone quarries of southern Germany, especially those that have yielded fossils like Archaeopteryx, are renowned for their exceptional preservation. Cearumimus joins this legacy as another remarkable example of how delicate structures can be fossilized under the right conditions. The fine-grained sediment in which the fossil was embedded allowed for the preservation of soft tissues and integument that are rarely seen in the fossil record. These conditions provided paleontologists with a rare opportunity to observe minute details of early feather development, such as the texture, pattern, and placement of the filaments. Such insights are critical in understanding the step-by-step evolutionary process that led from simple skin filaments to complex flight feathers. As more feathered theropods like Siuromyrmus come to light, the image of what a dinosaur looked like continues to change. No longer viewed as scaly, reptilian creatures exclusively, many theropods are now understood to have been adorned with various forms of feathers. This radical shift in perception has reshaped the way scientists reconstruct prehistoric ecosystems and the animals within them. The discovery of Siuromyrmus has helped to extend the evolutionary timeline of feathers, pushing their origin further back and suggesting that even the earliest branches of the theropod tree may have shared this trait. It also encourages the idea that feathers were not just a byproduct of avian evolution, but a central feature of dinosaur biology. In conclusion, Siuromyrmus albus duoferi offers a fascinating look into the deep history of feathers and the diverse evolutionary experiments of the Jurassic period. Its remarkably preserved remains serve as a time capsule, capturing a moment when feathers were not yet meant for flight, but were already beginning to shape the lives of dinosaurs. From its squirrel-like tail to its place in the growing family of feathered theropods, Siuromyrmus reveals that the story of feathers is not confined to birds alone, but is instead woven through the entire history of theropod dinosaurs. As new discoveries continue to reshape our understanding, fossils like Siuromyrmus remain vital pieces in the puzzle of prehistoric life. Part 18. Microraptor. In the wind-swept expanses of Patagonia, Argentina, a discovery was made that would challenge preconceptions about where bird-like dinosaurs once lived. Microraptor gonzalezorum, named after the La Boucherie fossil site where it was uncovered, emerged from late Cretaceous rocks dating to roughly 90 to 95 million years ago. Small, lightweight and equipped with long arms and a slender snout filled with tiny sharp teeth, Microraptor looked as if it had stepped out of a scene from prehistoric northern forests. Yet here it was in South America, far from the feathered theropods more commonly associated with Asia. Its discovery not only expanded the global range of dromaeosaurids, but also hinted at a broader distribution and diversity of feathered dinosaurs than previously imagined. Unlike many of its dromaeosaurid cousins, Microraptor was relatively small and gracile, likely weighing no more than 15 kilograms and measuring around 1.5 meters in length. Its skeletal features reveal adaptations for speed and agility, long hind limbs for quick bursts of motion, and a long, stiff tail for balance, helping it maneuver through dense vegetation or rocky outcrops. Its feet, equipped with the famous retractable second toe claw common to dromaeosaurids, hint at a predatory lifestyle. However, the shape and size of its claws suggest that it may have used them more for grasping or pinning rather than for delivering fatal kicks like its larger relatives, such as Velociraptor. These anatomical distinctions have opened new discussions about the behavioral diversity within the dromaeosaurid family. Perhaps the most striking feature of Microraptor is its long, narrow skull with a tapered snout lined with over 120 small, recurved teeth. These teeth lacked serrations, a characteristic that sets it apart from many other dromaeosaurids. Instead of slicing flesh, these needle-like teeth were likely adapted for capturing small, slippery prey, such as lizards, insects, or perhaps even fish. This feeding adaptation indicates a more delicate, precision-based hunting strategy. It also underscores the ecological diversity among dromaeosaurids. Some were robust hunters of larger prey, while others, like Microraptor, evolved to exploit very different ecological niches. The discovery of such variation in feeding strategies among closely related species paints a picture of ecosystems full of specialization and interdependence. Feathered impressions have not been directly found with Microraptor fossils, but it is widely accepted among paleontologists that it would have had feathers. As a basal dromaeosaurid, and given the strong phylogenetic relationship with other feathered species like Microraptor and Velociraptor, the presence of feathers on Microraptor is inferred with confidence. These would likely have included a downy coat for thermoregulation and possibly longer quill-like feathers on the arms and tail, though not for flight. In this way, Microraptor further supports the theory that feathers were a widespread and ancient trait among theropods, predating the evolution of powered flight. Their original purposes, insulation, display, camouflage, or even brooding behavior, may have laid the groundwork for the later evolution of flight in avian dinosaurs. Its discovery in South America was significant because it represented the first clear evidence of dromaeosaurids in Gondwana, the ancient southern supercontinent. Until then, most dromaeosaurid fossils had been unearthed in Eurasian territories like Asia and North America. The presence of Microraptor in Argentina suggests that the dromaeosaurids were not only more geographically widespread than once assumed, but also that they had a longer evolutionary history than previously documented. This insight has prompted re-evaluations of continental dinosaur migration patterns and biogeographical isolation events during the Mesozoic. The division between Gondwanan and Eurasian lineages may have driven the evolution of distinct traits, leading to the unique morphology observed in Microraptor. The environment that Microraptor inhabited was part of what is now known as the Candeleras Formation, an ancient ecosystem dominated by semi-arid floodplains interspersed with river systems and rocky outcrops. This region supported a variety of fauna, including large sauropods, avian theropods, turtles, and early mammals. Microraptor, being small and agile, likely moved through the underbrush, darting between larger animals, seizing opportunities to snatch prey from crevices or along water's edge. Its relatively lightweight build and specialized teeth allowed it to exploit resources that larger carnivores couldn't, reducing competition and giving it an ecological advantage in its particular niche. From an evolutionary perspective, Microraptor provides a vital link between early feathered dinosaurs and more derived bird-like forms. Its skeletal structure, particularly the elongated arms, stiffened tail, and inferred feathering, shares many characteristics with both basal dromaeosaurs and early avialans. This mix of traits supports the idea that the boundary between birds and non-avian dinosaurs is more blurred than previously thought. Species like Microraptor help clarify how feathers and other avian features evolved gradually and in stages, with many feathered dinosaurs exhibiting some but not all of the adaptations seen in modern birds. This continuum of features demonstrates the complex evolutionary pathway that led from grounded theropods to the skies above. Despite its ancient origins, Microraptor continues to inspire modern science. Advanced imaging and analysis techniques, such as micro-CT scanning and histological sampling, have enabled paleontologists to study internal structures like bone growth and brain cavity morphology. These insights allow scientists to infer growth rates, metabolism, and even sensory capabilities. For example, comparisons of the inner ear structure suggest that Microraptor had good balance and spatial awareness, traits consistent with agile, active predation. Ongoing studies of its limb proportions and claw curvature also hint at possible arboreal behavior, raising intriguing questions about whether some dromaeosaurs were tree climbers, and if arboreal habits played any role in the origin of flight. In total, Microraptor gonzalezorum stands as a testament to the unexpected diversity and adaptability of feathered dinosaurs across ancient Earth. With its sleek form, specialized teeth, and inferred feathered body, it represents a different side of the dromaeosaurid lineage, one built not on brute strength, but on speed, precision, and evolutionary nuance. Found far from the feathered fossils of China, Microraptor reinforces the idea that the evolution of feathers, small body sizes, and agile movement was a widespread and deeply rooted phenomenon among theropods. Its story continues to illuminate the broader narrative of dinosaur evolution, adding color, complexity, and elegance to the prehistoric world. Part 19. Anzus. The discovery of Anzu williae offered a vivid and almost mythical creature to the fossil record of late Cretaceous North America. Nicknamed the chicken from hell for its bizarre appearance, Anzu looked like something between a cassowary and a velociraptor, yet it stood in its own category of dinosaur uniqueness. Unearthed from the Hell Creek Formation in the Dakotas, this oviraptorosaur quickly captured public and scientific fascination with its combination of a toothless beak, long arms with massive claws, a crest atop its head, and feathers inferred from close relatives. It belonged to a group of theropods known as chaenagnathids, a branch of the oviraptorosaurs, a lineage already known for their strange bird-like features. Yet Anzu stood out for its size and the completeness of its fossil remains, providing the most detailed look yet at these enigmatic animals in North America. Anzu was among the largest known oviraptorosaurs, measuring about 3.5 meters in length and weighing approximately 200 to 300 kilograms. This sizable dinosaur had long hind limbs that suggested it was a fast and agile runner, with a build that was more gracile than bulky. Its long neck curved gracefully upward toward a relatively small head, which lacked teeth and ended in a broad parrot-like beak. A prominent crest adorned its skull, similar in appearance to those of modern cassowaries, though its function remains speculative. It may have been used in visual display, species recognition, or sexual selection. This blend of anatomical traits, graceful, bird-like features paired with a dinosaurian frame, creates a fascinating window into the evolutionary bridge between non-avian theropods and early birds. The anatomy of Anzu suggests a versatile and opportunistic lifestyle. Its strong forelimbs and large claws may have been used for digging, grasping, or even manipulating objects in its environment. Its beak, lacking any obvious specializations for meat or plant matter, hints at an omnivorous diet. It may have consumed small vertebrates, eggs, insects, fruit, and plant material, depending on availability. The diversity of food sources in the Hell Creek ecosystem, including lush vegetation and smaller animals, would have provided a rich buffet for a dinosaur with generalist feeding habits. This dietary flexibility might explain the success and adaptability of chaenagnathids across different parts of the Cretaceous world, from Asia to North America. The fossil evidence for Anzu comes from at least 3 partial skeletons discovered in close proximity, offering a rare opportunity to reconstruct much of its body. This completeness allowed paleontologists to study its limb proportions, vertebrae, and pelvis in detail, shedding light on its movement and lifestyle. The structure of its hind legs, especially the elongate metatarsals and slender toes, suggests it was a capable and possibly swift runner, adapted for covering ground efficiently. Its long tail, stiffened by elongated bones, would have served as a counterbalance, aiding stability during high-speed pursuits or quick directional changes. Despite its size, Anzu was likely a nimble creature, more suited to dashing across open landscapes than lumbering through dense forests. Feathers are a critical piece of the puzzle when interpreting Anzu. While no direct feather impressions were preserved with the known specimens, its close relatives both in North America and Asia clearly possessed feathers, and the evolutionary proximity makes it nearly certain that Anzu did too. These feathers may have covered much of its body, providing insulation and possibly playing a role in display or mating behavior. The presence of a crest and a likely plume of feathers might have made Anzu a truly eye-catching animal, with striking patterns or colors used to communicate dominance, attract mates, or deter rivals. In this way, Anzu shares a conceptual kinship with modern birds, where feathers serve not just functional but also social roles. The environment in which Anzu lived was dynamic and rich with life. The Hell Creek Formation is well known for preserving a diverse snapshot of late Cretaceous ecosystems, including towering tyrannosaurs, armored ankylosaurs, fast-moving ornithomimids, and early mammals. It was a time of ecological complexity, with river systems, floodplains, and forested areas providing varied niches. In this tapestry, Anzu may have occupied a role similar to that of modern omnivorous birds, such as ground hornbills or emus, striding through its environment, feeding on whatever it could find, and interacting with a host of other creatures. Its adaptation to a terrestrial lifestyle allowed it to exploit both open and forested terrain, and its generalized diet made it resilient in a changing world. One particularly interesting aspect of Anzu is how its discovery redefined previous fragmentary fossils. Prior to the discovery of its nearly complete remains, many isolated bones of canignathids had been found in North America, but their relationships and appearance were poorly understood. With the discovery of Anzu, paleontologists could now re-examine those fragments and recognize them as parts of similar animals. This helped to clarify the diversity and distribution of canignathids on the continent, showing that they were not rare outliers, but rather active participants in the late Cretaceous ecosystems. Anzu thus became a reference species, a keystone for understanding a once murky branch of dinosaur evolution. The implications of Anzu's existence stretch beyond anatomy and classification. Its presence in North America supports the idea of biogeographic exchange between Asia and North America during the Cretaceous. Oviraptorosaurs were once thought to be largely restricted to Asia, where many famous species like Sittipati and Khan have been found. The similarities between these Asian species and Anzu suggest that there was gene flow or migration between continents, perhaps across land bridges that existed during periods of lowered sea levels. These patterns help paint a picture of a world where dinosaurs were not strictly regional, but were capable of wide dispersal and adaptive radiation. Anzu represents more than just another feathered dinosaur. It symbolizes the growing understanding of just how complex, strange, and interconnected the world of dinosaurs was. With its powerful legs, probable feathers, long arms, expressive crest, and likely omnivorous habits, it adds a layer of depth to the concept of theropod evolution. It reminds us that dinosaurs were not just giant reptiles but dynamic, bird-like creatures with a wide array of forms and behaviors. As more specimens are discovered and studied, Anzu will continue to stand as a dramatic example of how even the most outlandish fossil finds can help reconstruct a vivid and nuanced vision of the prehistoric past. Part 20. Ornithomimus. The name ornithomimus means bird mimic, and this dinosaur lived up to its title in remarkable fashion. Found primarily in late Cretaceous deposits of North America, Ornithomimus was one of the most bird-like non-avian dinosaurs ever discovered. With a slender, lightweight body, long legs built for speed, a toothless beak, and evidence of feathers, it presented an evolutionary portrait that closely mirrored traits found in modern ostriches. This resemblance was more than superficial. The skeletal and anatomical similarities point to convergent evolution, where unrelated species develop similar features due to occupying similar ecological roles. In the case of Ornithomimus, it was likely a fast, omnivorous ground dweller, adapted to open environments where agility and keen senses offered major survival advantages. Measuring up to 3.5 to 4 meters in length and standing around 2 meters tall at the hip, Ornithomimus was a fairly large animal in its own right, though it had a light build that emphasized speed over brute strength. Its limbs were especially well adapted for running, long, powerful hind legs with well-developed muscles and elongate metatarsals, reminiscent of those seen in modern cursorial birds. Its hands, tipped with long, curved claws, were also quite mobile, suggesting grasping capabilities, perhaps for manipulating food or interacting with objects in its environment. The head was small and perched atop a long neck, giving the animal an excellent range of vision. Its beak-like mouth had no teeth, which likely restricted it to a diet composed of soft vegetation, fruit, small animals, or even insects, anything it could swallow without chewing. Fossil evidence suggests Ornithomimus may have been covered in feathers, making it one of the clearest examples of feathered dinosaurs discovered in North America. In particular, fossilized remains from adult individuals have shown impressions of long filamentous feathers on the arms, suggesting the presence of feathered structures that may have resembled primitive wings. However, these wings were likely non-functional for flight. Their presence may have had other roles, such as display during mating rituals, thermoregulation, or brooding behaviors. These feathers, along with body covering likely composed of downy filamentous structures, offer insights into the evolutionary experiments nature conducted before perfecting flight-capable wings in later avian forms. Juvenile Ornithomimus specimens showed something even more intriguing: an apparent lack of arm feathers. This has led some paleontologists to propose that feather development in this species was linked to sexual maturity. In other words, young individuals were mostly covered in downy insulation, while adults developed more elaborate feathering, potentially for mating displays or social signaling. This developmental pattern closely mirrors what is seen in many modern birds, where plumage becomes more ornate and differentiated with age. Such a parallel offers valuable clues into the behavioral complexity of Ornithomimus, suggesting that it may have lived in dynamic social groups where visual cues played an important role. The environment in which Ornithomimus lived was diverse and teeming with life. During the late Cretaceous, North America was split into eastern and western landmasses by a shallow inland sea. Ornithomimus fossils are predominantly found in the western part, in what is now Alberta and other regions of western Canada and the United States. These areas were characterized by floodplains, river deltas, and rich forests that supported a wide array of plant and animal species. In such ecosystems, Ornithomimus would have encountered both predators and competitors. Its speed and awareness likely helped it survive in a landscape shared with large theropods like Tyrannosaurus rex, as well as smaller predators, herbivores, and early mammals. Speed was probably one of Ornithomimus's greatest assets. Estimates suggest that it could run at speeds exceeding 40 kilometers per hour, making it one of the fastest dinosaurs known. This velocity, combined with its long legs and streamlined form, suggests a lifestyle that depended heavily on fleeing danger rather than confronting it. The structure of its feet, with 3 strong toes, offered balance and traction, perfect for rapid sprints across open terrain. Its long tail would have served as a counterbalance, helping stabilize the body during sudden turns or evasive maneuvers. This kind of agility would be especially important in the wide plains and open habitats where Ornithomimus thrived. The brain of Ornithomimus was relatively large compared to its body size, and this has led some researchers to speculate about its intelligence. While not on par with modern birds like crows or parrots, its neural capacity was likely sufficient for complex behaviors, including social interactions, problem-solving, and learning. The presence of a keen sense of vision and possibly hearing further suggests that it was a perceptive and alert animal. Such traits would be essential in a social species, where recognizing individuals, interpreting behaviors, and responding to environmental stimuli quickly would all play roles in survival and reproduction. Feathered, swift, and seemingly intelligent, Ornithomimus also plays an important role in understanding the evolutionary relationship between theropods and birds. As a member of the Ornithomimosaurs ostrich mimics, this group shows how far convergent evolution can go. These dinosaurs, while not directly ancestral to birds, evolved similar body plans due to occupying similar niches. They blur the lines between what is considered bird and what is still firmly dinosaur, demonstrating that bird-like features were more widespread in the dinosaur lineage than once believed. Ornithomimus, in this context, becomes an example of how evolutionary pressures repeatedly arrive at similar solutions for survival. The continued discovery and study of Ornithomimus fossils help refine the timeline and complexity of feather evolution. Its well-preserved remains from Canada and the US bridge a geographical gap in the fossil record, showing that feathered theropods were not exclusive to Asia. This broadens the scope of feather development across multiple dinosaur lineages and continents. Furthermore, it challenges older, reptile-centered views of dinosaurs and supports a more dynamic, bird-like model of behavior and appearance. With each new fossil, Ornithomimus becomes more than just a bird mimic. It stands as a symbol of transition, adaptability, and the fascinating mosaic of traits that define the dinosaur-bird connection. Part 21. Hesperornis. Hesperornis was a fascinating bird-like dinosaur that roamed the Earth during the late Cretaceous period, around 85 to 70 million years ago. It lived in what is now North America, mostly in marine environments, and was a master of the water. Hesperornis is often classified as a primitive bird due to its combination of reptilian and avian characteristics. What makes this species particularly interesting is the way it bridged the gap between dinosaurs and modern birds. It had a body shaped for life in water, much like a diving bird today, and its skeletal structure showed distinct adaptations to both swimming and flying. Unlike many other prehistoric birds, Hesperornis was flightless. Its wings were small and nearly useless for flight, but that didn't hinder its ability to thrive in the water. The wings were thought to be used for balance and steering while swimming, much like the flippers of modern penguins. Its legs, which were strong and muscular, were positioned at the rear of its body, a characteristic that helped propel it through the water with great efficiency. This unique adaptation made it a skilled predator, capable of catching fish and other aquatic creatures with ease. Hesperornis had long, sharp teeth embedded in its jaws, a feature that set it apart from many modern birds. While it wasn't the largest of its kind, it certainly made up for its size with its specialized hunting techniques. Its teeth were perfect for grasping slippery prey, and the bird would likely have spent much of its time diving for fish in the seas. Some scientists believe that its hunting methods may have resembled those of modern seabirds, such as cormorants, which dive beneath the surface to catch their food. With its sleek body and sharp beak, Hesperornis was a formidable hunter in its aquatic environment. The fossil record for Hesperornis provides a detailed picture of this creature's anatomy and lifestyle. One of the most remarkable features of Hesperornis is its large, flattened, toothless beak, which allowed it to catch and hold fish while underwater. Unlike many other prehistoric birds, Hesperornis had a highly specialized diet focused primarily on fish, making it an important part of its ecosystem's food chain. Its long, sharp beak helped it grip its prey firmly, preventing it from escaping while the bird returned to the surface to swallow it. Despite its reliance on the sea, Hesperornis was not a true marine bird like today's penguins or puffins. It was still a part of the dinosaur family, and its evolutionary lineage shows a clear connection to theropod dinosaurs. Paleontologists have determined that Hesperornis was part of a larger group of prehistoric birds known as the Enantiornis, a diverse group that lived during the Mesozoic era. These birds were characterized by their primitive features, which included teeth, clawed wings, and a tail that was often longer than that of modern birds. Hesperornis, with its combination of ancient traits and newly developed avian features, provides crucial insight into the early evolution of birds. What sets Hesperornis apart from other early birds is its ability to adapt to a completely different environment: the water. While most early birds were arboreal or terrestrial, Hesperornis evolved to be an expert swimmer, using its body to navigate the sea. It had long, slender legs and webbed feet that acted like powerful paddles, propelling it through the water with great speed. Its ability to hunt in the water made it a highly effective predator in its environment, and it likely spent much of its time near the shore, diving for fish and small marine creatures. Interestingly, Hesperornis has also provided some insights into the evolution of modern birds, especially in terms of flight and migration. Though it did not fly, its descendants played a role in the development of flightless birds like penguins and some modern seabirds. The evolutionary pathway that led to birds capable of both flight and waterfowl-like behaviors can be traced back to creatures like Hesperornis, which was clearly on the cutting edge of avian development. The close examination of this bird has allowed paleontologists to better understand how flightless birds came to be and how their anatomy and behaviors adapted to suit their environments. The fossilized remains of Hesperornis are some of the most well-preserved early bird fossils ever discovered. In fact, Hesperornis fossils are often found in marine deposits, which suggests that the bird lived in coastal areas or near islands where it could easily access food sources. These fossils have provided invaluable information about the lifestyle and habits of this prehistoric bird. From its specialized skeletal structure to its diet and hunting strategies, every aspect of Hesperornis has helped shape our understanding of early bird evolution. One of the most fascinating aspects of Hesperornis is its connection to the ongoing evolution of birds today. Though Hesperornis itself was not a direct ancestor of modern birds, its existence highlights how birds evolved from dinosaurs and adapted to new niches. Today, birds are among the most successful and diverse animals on the planet, with species that live in every corner of the Earth. Understanding creatures like Hesperornis sheds light on the complex process of evolution, showing how birds evolved from small, feathered dinosaurs to the incredible array of species we see today. While Hesperornis may no longer exist, its legacy is far-reaching. This early bird not only teaches us about the evolution of birds, but it also serves as a reminder of the dynamic changes that occurred during the Mesozoic era. Through the study of creatures like Hesperornis, paleontologists are able to piece together the incredible story of life on Earth, from the rise of the dinosaurs to the eventual appearance of birds. Each new discovery brings us closer to understanding the ancient world and the life forms that once ruled the skies, the seas, and the land. Part 22. Pelecanimimmus. Pelecanimimmus was an intriguing dinosaur that lived during the early Cretaceous period, roughly 120 million years ago. Fossils of this bird-like dinosaur were discovered in what is now Spain, making it one of the most significant prehistoric creatures from Europe. Pelecanimimmus was relatively small, measuring only about 2.5 meters in length, and it was likely a very agile and fast runner. What makes this species particularly fascinating is the combination of its bird-like features, including a long, slender body and small, delicate hands, with characteristics that link it directly to its dinosaur ancestors. Pelecanimimmus belongs to a group of dinosaurs known as the Ornithomimidae, which are sometimes referred to as ostrich dinosaurs. These creatures are named after modern ostriches due to their long legs, long necks, and small heads. However, unlike ostriches, Pelecanimimmus had some distinctive features that set it apart from modern flightless birds. Its most notable characteristic was its toothless beak, which gave it a very bird-like appearance, making it one of the early examples of dinosaurs with beaks, a feature that would become more prominent in the evolution of modern birds. The skeletal structure of Pelecanimimmus reveals its highly specialized adaptations for a fast, active lifestyle. Its long legs were built for speed, allowing it to cover large distances quickly. Its body was lightweight, which helped it maintain its agility, and its long tail provided balance while running. This dinosaur's build was clearly optimized for running, and it is thought that Pelecanimimmus likely hunted or scavenged small prey, and perhaps even foraged for plant matter, similar to the feeding habits of modern birds like ostriches or emus. Its long, powerful legs would have enabled it to chase down small animals, such as insects or small reptiles, in the environments it inhabited. One of the most interesting aspects of Pelecanimimmus is its relationship to the origin of birds. As a member of the Ornithomidae family, it shares several key traits with early birds. The presence of a toothless beak in Pelecanimimmus is a notable feature in this regard. While many dinosaurs, including some theropods, retain sharp teeth throughout their evolution, some species began to evolve beaks instead, a feature that would later become a hallmark of modern birds. Pelecanimimmus is an example of how certain dinosaur groups began to adapt to a more bird-like lifestyle even before the full evolution of flight. Another distinctive feature of Pelecanimimmus was its small but powerful hands. Unlike the tiny hands of many other theropods, the hands of Pelecanimimmus were relatively large and well-suited for grasping. This indicates that despite its running adaptations, it may have had some ability to manipulate objects or capture prey using its hands. The sharp claws on its fingers would have made it an effective predator when needed, and it's possible that it could have used them to catch small animals or defend itself from larger predators. The environment in which Pelecanimimmus lived was vastly different from the one modern birds inhabit today. During the early Cretaceous, the Earth was much warmer and wetter, with lush vegetation and diverse ecosystems. Pelecanimimmus would have roamed through forests, wetlands, and coastal regions, where it likely encountered a variety of other prehistoric creatures. Its lightweight frame and swift movements would have made it a capable scavenger or hunter, able to evade larger predators and thrive in its habitat. Pelecanimimus is a part of a larger group of dinosaurs known for their bird-like characteristics, including other members of the Ornithomimidae family. These dinosaurs are often regarded as the bird mimics of the Mesozoic era, as they shared many traits that would eventually be passed down to modern birds. The evolutionary transition from theropod dinosaurs like Pelecanimimus to birds is a crucial area of study for paleontologists, as it provides insight into how some dinosaurs evolved into the avian species that dominate our world today. The discovery of Pelecanimimus is significant because it sheds light on the complex relationship between dinosaurs and birds. Paleontologists often look for specific skeletal features that indicate the presence of flight or bird-like behavior, and the study of Pelecanimimus provides an important link in this chain. For example, its bipedal stance, long legs, and beak are features shared with many modern birds, highlighting the early stages of the evolutionary process that would eventually lead to the appearance of flight in later bird species. Despite its bird-like characteristics, Pelecanimimus was not capable of flight. This is a reminder that the evolution of birds from dinosaurs was a gradual process, involving many steps and adaptations. Pelecanimimus provides a glimpse into one of those steps, where certain traits, such as a beak and a lighter body structure, began to appear in non-flying dinosaurs. Over millions of years, these features would eventually evolve into the fully fledged flight capabilities seen in modern birds. The fossilized remains of Pelecanimimus offer a rare opportunity to explore the early stages of bird evolution. This species serves as an important marker in the history of vertebrate evolution, showing how dinosaurs gradually adapted to environments that favored lighter, faster, and more agile creatures. Though it may not have been able to take to the skies like modern birds, Pelecanimimus was clearly a creature with remarkable adaptations, laying the groundwork for the birds that would follow. Its fossils continue to provide valuable insight into the world of the Mesozoic era and the ancient creatures that once roamed it.